When spacecraft first sent back detailed images of other worlds, scientists expected surfaces shaped by familiar processes like those on Earth, perhaps with craters added. What arrived instead showed landscapes that had no counterpart anywhere on our planet. Terrains formed by processes we had never witnessed. Materials that behave in ways Earth's rocks and ice never do. The solar system revealed itself as a collection of surfaces stranger than science fiction had imagined. Each world sculpted by its own unique combination of temperature, pressure, gravity, and chemistry. These alien landscapes wait in silence across billions of miles, some revealed by flyby missions that glimpsed them only briefly, others mapped in detail by orbiters that circled for years. The surfaces persist, whether cameras observe them or not, maintained by ongoing processes or frozen in ancient configurations that have not changed in millions of years. Tonight, we explore some of these remarkable terrains, moving freely through the solar system to visit places where the ground beneath you would feel utterly unfamiliar, where familiar words like ice and lava take on meanings Earth never demonstrates. You are listening to the Drowsy Astronaut, where we take our time with the details that make the cosmos quietly extraordinary, never rushing, always exploring deeply. If you are settling in for the night, wherever you happen to be, you might leave a comment about where you are listening from, what draws you to space science. Whether you are a long-time astronomy enthusiast or simply curious about what exists beyond Earth. If this slow journey through our solar system's most remarkable facts brings you some calm or fascination, the like button and subscribe option are there. Mercury, the closest planet to the Sun, experiences temperature swings more extreme than any other world in the solar system, with noon reaching 800 degrees Fahrenheit and midnight dropping to -300 degrees. Near its north pole sits a feature called Pantheon Fossae, though the name gives no hint of how strange it appears from orbit. The formation resembles a massive spider, with a central irregular depression surrounded by more than 100 fractures radiating outward like legs extending in all directions. Some of these fractures stretch for hundreds of miles across the cratered surface, creating a pattern visible from space, a geometry that seems almost deliberate, though it formed from natural processes. Scientists believe the spider formed when a large impact struck Mercury's surface, creating the central depression and sending shock waves through the crust that cracked it in radiating patterns. Volcanic activity may have followed, with magma forcing its way through some of the fractures and causing additional stress that extended the pattern further. The combination created something unique in the solar system, a formation that looks planned but arose from the violent intersection of impact energy and volcanic response. The spider sits frozen in place now, preserved in the airless environment, where no erosion wears away the details, waiting as it has for billions of years. Far from Mercury, in the cold outer solar system, Saturn's moon Triton presents a completely different kind of alien surface, one that mirrors Earth in surprising ways, yet uses entirely different materials. Triton possesses the only stable bodies of surface liquid anywhere beyond Earth, but these lakes contain not water, but methane and ethane, hydrocarbons that would be gases at Earth's temperatures. The liquid pools in depressions near the poles, creating lakes and seas with shorelines visible in radar images, edges where liquid meets solid ground. The largest, Kraken Mare, covers an area larger than the Caspian Sea, and in places reaches depths that may exceed 900 feet. The shorelines change with Titan seasons, which unfold across Saturn's long year of 29 Earth years. During winter, at one pole, the lakes fill with methane raining from clouds, the liquid accumulating in basins and spreading along channels that drain the surrounding terrain. As that pole tilts into summer, the methane evaporates, shrinking the lakes and eventually causing some to disappear entirely, while the opposite pole enters winter and its own lakes begin to fill. The landscape undergoes a slow hydrological cycle driven not by water but by methane, creating beaches and coastlines where the sand consists of ice harder than granite at temperatures around -290 degrees Fahrenheit. Standing on one of these shorelines would present a view both familiar and utterly alien, a liquid surface lapping at a solid shore. But the liquid would be transparent methane at a temperature that would freeze you instantly. The atmosphere above would glow orange from organic haze, dimming the already distant sun to a faint glow barely distinguishable from bright moonlight. Waves would move in slow motion through the thick air and low gravity, taking far longer to travel across the lake than water waves on Earth. The scene would feel like a dark, cold parody of an Earth beach, similar in structure, but different in every detail. Venus, closer to the Sun than Earth, and similar in size, hides its surface beneath clouds so thick that no telescope can penetrate them to see the ground below. When radar mapped the surface from orbit, it revealed volcanic features in abundance, including structures that appear nowhere else in quite the same form. Scattered across the plains sit dozens of large domes, each one perfectly circular when viewed from above, flat-topped like enormous pancakes, ranging from 30 to 65 kilometers in diameter. These pancake domes formed when extremely thick, viscous lava oozed up from below and spread outward slowly, too thick to flow far, creating broad circular mountains with gentle slopes and flat summits. The lava that formed these domes differed from typical basaltic lava on Earth, possibly richer in silica or other compounds that increased its viscosity dramatically. When it emerged onto the surface, it spread like cold honey, advancing slowly outward from the vent in all directions with equal resistance, creating the circular shape. The flat top suggests the lava formed a crust, while the interior remained molten, and when the eruption ended, the molten interior drained away or solidified, leaving the surface flat rather than peaked. Some domes show cracks radiating from the center or concentric fractures circling the summit, evidence of cooling and stress after the eruption ceased. These domes sit on a surface where the temperature never drops below 850 degrees Fahrenheit, and the atmospheric pressure exceeds 90 times Earth's pressure at sea level. The environment would crush and melt most materials we consider durable, and the thick carbon dioxide atmosphere creates a greenhouse effect so powerful that Venus became the hottest planet, despite Mercury being closer to the Sun. The pancake domes formed in this hellish environment and remain there still, preserved because volcanic activity on Venus may have paused or slowed in recent geological time, leaving these structures as evidence of an earlier, more active period. Jupiter's moon Io presents yet another extreme, a world so volcanically active that its surface changes measurably between spacecraft visits, constantly being repaved by eruptions. The volcanic activity arises not from internal radioactive decay like Earth's, but from tidal heating caused by Jupiter's immense gravitational pull, flexing Io as its orbit brings it closer and farther from the giant planet. This continuous flexing generates enough heat to keep much of Io's interior molten, and that molten material erupts constantly from hundreds of active volcanoes. The eruptions deposit sulfur and sulfur compounds across the surface, creating the most colorful solid surface in the solar system. The colors range from bright yellow to orange to red to dark brown and nearly black, each shade representing sulfur in different chemical forms or at different temperatures. Fresh sulfur dioxide frost falls as pale yellow snow near active volcanic vents, gradually darkening as radiation from Jupiter's magnetosphere bombards it and chemical reactions alter its structure. Older deposits shift to orange and red, while the oldest or most heavily processed regions turn dark brown or black. The entire moon resembles a painter's palette, with colors layered and mixed in patterns that reflect the ongoing volcanic resurfacing and radiation processing. Some regions on Io appear to glow faintly even in shadow, their surfaces heated above the surrounding terrain by volcanic activity just beneath the crust. Lava lakes churn visibly in some calderas, their surfaces constantly overturning as cooler crust sinks and hotter material rises. The volcanic plumes shoot sulfur dioxide gas and particles hundreds of miles above the surface, where some material escapes Io's gravity entirely and feeds a torus of charged particles orbiting Jupiter along Io's orbital path. The moon exists in a state of continuous geological chaos, never settling, always erupting, its surface being replaced every million years or so by fresh volcanic deposits. Enceladus, a small moon of Saturn only 300 miles in diameter, should be geologically dead, according to conventional understanding of how rocky bodies work. Small objects cool quickly and lose their internal heat, becoming frozen and inactive within a few 100 million years of formation. Yet Enceladus displays some of the most dramatic ongoing geological activity anywhere in the solar system, all concentrated at its south polar region. 4 parallel fractures cut across the South Pole, each about 80 miles long and a mile wide, glowing blue in color-enhanced images due to fresh ice exposed at the surface. Scientists nicknamed these fractures the tiger stripes, and from them erupt continuous plumes of water vapor, ice crystals, and organic molecules shooting material hundreds of miles above the surface. The Cassini spacecraft flew through these plumes multiple times, collecting samples and analyzing them, finding water, salt, silica particles, and simple organic compounds. The plumes originate from a global ocean that lies 20 to 30 miles beneath the ice shell, with the tiger stripes representing fractures where tidal heating from Saturn's gravity has thinned the ice enough to allow the pressurized ocean to break through. The water erupts into the vacuum of space, immediately freezing into tiny ice particles that either fall back to the surface or escape into orbit around Saturn. The eruption rate varies with Enceladus's orbital position, stronger when the moon is farthest from Saturn and slightly weaker when closer, demonstrating that tidal forces directly control the geyser activity. The fractures themselves appear warmer than the surrounding ice by about 200 degrees. Though warmer, still means temperatures around -120 degrees Fahrenheit compared to the surrounding -330 degrees. The tiger stripes mark the warmest regions on any icy moon, places where internal heat reaches the surface and creates conditions unlike anything elsewhere on such a small, frozen world. The fresh ice particles from the geysers constantly settle onto the surface, coating everything in a thin layer of pristine ice that makes Enceladus the brightest object in the solar system. Pluto, the distant world once considered the ninth planet and now classified as a dwarf planet, revealed its surface in detail only when New Horizons flew past in July 2015. Among the many surprises was a region unlike anything seen before. A terrain of jagged ice blades standing upright across large areas, each blade rising hundreds of feet above the surrounding plain. These blades consist of methane ice that has sublimated and redeposited repeatedly over millions of years, with the shaded sides of each blade protected from sublimation, while the sunlit sides slowly vaporize. The process creates tall, thin ridges, aligned roughly north-south, all pointing in the same direction, like rows of immense knife edges. The blades can reach heights exceeding 500 meters in places, taller than skyscrapers, and they stand so closely spaced that the terrain would be completely impassable to any rover or lander. Walking through this region would be impossible, each step requiring climbing over or between vertical ice walls that extend in unbroken lines toward the horizon. The formation process requires very specific conditions, a combination of the right temperature, atmospheric pressure, and sunlight angle that apparently exists only on Pluto and possibly on a few other distant ice worlds. The blades grow slowly, adding height over millions of years as the methane ice sublimates from horizontal surfaces and redeposits on vertical ones, where sunlight strikes at a lower angle. From orbit, the bladed terrain appears as a textured surface, with parallel lines creating a striated pattern across hundreds of square miles. The formation sits near Pluto's equator, where sunlight strikes at varying angles throughout the dwarf planet's long year, creating the conditions necessary for differential sublimation. The ice in these blades remains pristine, protected from the darkening effects of radiation by the continuous sublimation and redeposition that removes the surface layer and exposes fresh ice beneath. The terrain stands as evidence of processes operating on timescales incomprehensible to human experience. Geography shaped over millions of years by the patient work of sublimation and deposition. Mars displays evidence of processes that may still be active today, though the evidence remains ambiguous enough to fuel ongoing scientific debate. On many steep slopes in the southern mid-latitudes, dark streaks appear during warm seasons and fade during cold seasons, recurring in the same locations year after year. These features, called recurring slope lineae, start at the top of slopes and extend downward, growing longer during the warmest months, and then fading or disappearing entirely when temperatures drop. The streaks appear dark against the lighter Martian soil, suggesting either darkening of the surface material or removal of bright dust to expose darker material beneath. One hypothesis suggests the streaks form when salty water, kept liquid by dissolved salts despite temperatures below the freezing point of pure water, seeps from the subsurface and flows downslope before evaporating in the thin Martian atmosphere. The saltwater brine would darken the soil as it flowed, creating the observed streaks. An alternative explanation proposes that no liquid is involved, instead suggesting that seasonal changes in temperature cause dry sand or dust to flow downslope in small avalanches that remove bright surface dust and expose darker material. The debate continues because both explanations match some aspects of the observations, but face difficulties explaining other aspects. The streaks appear most commonly on slopes facing the equator, where sunlight strikes most directly and temperatures rise highest during summer months. They avoid shaded slopes and polar regions where temperatures remain consistently low. The seasonal timing matches the warmest period at each latitude, with streaks appearing first at higher latitudes in spring and later at lower latitudes in summer. This pattern suggests temperature plays a critical role, though whether it triggers liquid brine flow or dry granular flow remains unresolved. The streaks represent one of the tantalizing mysteries of current Mars science, a phenomenon we can observe recurring every year, but cannot yet definitively explain. Neptune's largest moon, Triton, orbits backwards relative to Neptune's rotation, one of the few large moons in the solar system with a retrograde orbit, suggesting it formed elsewhere and was later captured by Neptune's gravity. The surface displays several unusual features, including a region informally called cantaloupe terrain because its dimpled, pitted appearance resembles the skin of a melon. The terrain covers extensive areas near Triton's equator, consisting of oval depressions separated by raised ridges, creating a cellular pattern unlike anything on other moons. The depressions measure typically 20 to 30 kilometers across and sit a few hundred meters below the surrounding ridges. Scientists believe the cantaloupe terrain formed through a process called diapirism, where warmer, less dense material rose from below, while cooler, denser material sank, creating convection cells in the icy crust. The rising material would create the raised ridges, while the sinking material would form the depressions, and the pattern would persist as the ice froze into its current configuration. The process requires partially molten, or at least ductile ice, suggesting Triton's interior was warmer in the past, perhaps heated by tidal forces during the period when its orbit was being circularized after capture. The terrain preserves evidence of this ancient heating, frozen in place after the internal activity ceased. Triton also displays active geology in the form of nitrogen geysers, dark plumes erupting from beneath the surface and rising several miles above the moon before being carried downwind by Triton's thin atmosphere. These plumes create dark streaks across the pink nitrogen ice plains, marking where material from the eruptions settled onto the surface. The geysers provide clear evidence that Triton, despite its small size and distance from the sun, remains geologically active today, powered possibly by seasonal heating of subsurface nitrogen ice that vaporizes explosively when pressure builds sufficiently. The combination of cantaloupe terrain and active geysers makes Triton one of the most geologically interesting moons, a world shaped by processes both ancient and ongoing. These landscapes represent merely a sample of the extraordinary surfaces waiting across the solar system, each one shaped by local conditions into forms Earth never produces. The variety demonstrates how different combinations of temperature, pressure, composition, and energy create entirely different geological outcomes, and how much remains unfamiliar even in our own cosmic neighborhood. And while these surfaces show us what happens when rock and ice respond to alien conditions, the atmospheres above some of these worlds create phenomena just as strange. Weather patterns and atmospheric behaviors that challenge what we think we know about how air moves and clouds form. The atmospheres surrounding some worlds in our solar system create phenomena that make Earth's weather seem conventional by comparison, with wind speeds that exceed anything our planet generates and cloud formations that persist for centuries. These atmospheric behaviors arise from different heating patterns, rotation rates, and chemical compositions, each combination producing its own unique meteorology. When we look upward from the surface of various worlds, or observe them from orbit, the skies reveal processes that expand our understanding of what atmospheres can do. Venus rotates so slowly on its axis that one rotation takes 243 Earth days, longer than its orbital period of 225 days around the Sun. This creates an unusual situation where a Venusian year is shorter than a Venusian day, meaning the planet completes one orbit around the Sun before completing one full rotation on its axis. The slow rotation combines with the retrograde direction, meaning Venus spins backward compared to most planets, creating a sunrise and sunset pattern opposite to Earth's. On Venus, the sun would rise in the west and set in the east, if anyone could see the sun through the thick clouds that permanently obscure the sky. The time from one sunrise to the next, called a solar day, lasts 117 Earth days on Venus. During this long period, the same side of the planet faces the sun for weeks on end, before slowly rotating into darkness for another equally long night. The extreme length of the day-night cycle would create enormous temperature differences between the lit and unlit sides if Venus had a thin atmosphere, but the thick carbon dioxide blanket circulates heat so efficiently that temperatures remain nearly constant everywhere, day and night, equator and poles. The greenhouse effect traps so much heat that surface temperature differences amount to only a few degrees, despite the extreme day length. From the surface, if you could survive the crushing pressure and searing heat, the sky would glow a dim orange even at noon, the thick clouds scattering light into a perpetual twilight. The sun itself would never be visible, its light diffused through sulfuric acid clouds that extend from 30 to 40 miles above the surface. As evening approached, after weeks of daylight, the dimming would be so gradual as to be imperceptible, taking days for the light level to fade as the sun's position crept toward the western horizon. Night would bring not darkness, but a deep orange gloom, with the hot surface and atmosphere radiating thermal energy that creates a faint glow visible in infrared wavelengths. Neptune, the outermost major planet, receives sunlight 900 times weaker than Earth does, with the sun appearing merely as a very bright star in Neptune's sky. This minimal solar heating suggests the planet should have relatively calm weather, with weak winds, yet observations reveal the opposite. Wind speeds on Neptune reach 1,200 miles per hour, the fastest sustained winds measured anywhere in the solar system, exceeding hurricane force by factors of several times. These fierce winds blow in the same direction as Neptune's rotation, circling the planet in jet streams that persist in the upper atmosphere, despite the weak energy input from distant sunlight. The energy driving these winds comes not from the sun, but from Neptune's interior, which radiates about 2.6 times more energy than the planet receives from solar radiation. This internal heat source, left over from the planet's formation, or possibly generated by ongoing processes in the interior, rises through the atmosphere and creates convection currents that drive the wind patterns. The temperature difference between the warm rising gas and the cold upper atmosphere creates instability that manifests as powerful winds. Unlike Jupiter and Saturn, which rotate rapidly and create many alternating wind bands, Neptune rotates more slowly and produces fewer distinct jet streams, but those that exist blow with remarkable ferocity. Dark storm systems appear and disappear in Neptune's atmosphere over periods of years, observed first by Voyager 2 in 1989 when it detected the Great Dark Spot, a storm system larger than Earth. When the Hubble Space Telescope looked at Neptune several years later, the Great Dark Spot had vanished completely, but new dark spots had appeared elsewhere. These storms apparently form, persist for a few years, and then dissipate, unlike Jupiter's Great Red Spot, which has lasted for at least 3 centuries. The transient nature of Neptune's storms suggests a more dynamic atmospheric system than Jupiter's, with storm systems forming from localized conditions rather than from stable, long-lived circulation patterns. Saturn's moon Triton possesses an atmosphere thicker than Earth's, with surface pressure about 1.5 times what we experience at sea level. The atmosphere consists mostly of nitrogen like Earth's, but instead of oxygen as the second most common gas, Triton has methane making up about 5% of the atmosphere. This methane participates in a cycle remarkably similar to Earth's water cycle, evaporating from surface lakes, rising into the atmosphere, condensing into clouds, and falling as rain. Methane rain on Triton falls from clouds that form in the thick orange haze, layers, with individual raindrops growing larger than Earth raindrops because they fall through denser air and experience less aerodynamic stress. In Triton's thick atmosphere and low gravity, about 1/7 of Earth's, a methane raindrop can grow to a centimeter in diameter without breaking apart, roughly twice the size of the largest stable raindrops on Earth. These oversized drops fall slowly through the dense air, drifting downward at about half the speed of Earth rain, taking longer to reach the surface. When they strike the ground, they splash and flow just as water does on Earth, running downhill in streams that carve channels and feeding into rivers that eventually drain into the polar lakes. The similarity to Earth's hydrological cycle is striking, but everything happens at a temperature of -290 degrees Fahrenheit, where water ice is as hard as granite. The orange color that gives Triton its appearance comes from complex organic molecules called tholins that form high in the atmosphere when ultraviolet light from the sun breaks apart methane and nitrogen molecules. The fragments recombine into larger, more complex molecules that gradually settle downward through the atmosphere, creating layers of haze that obscure the surface completely in visible light. These organic particles give the atmosphere its color and scatter light in ways that create the perpetual twilight at ground level. Even at noon, the sun appears only as a vague glow through the thick haze, providing less than 1% of the sunlight Earth receives, creating a dim world of deep shadows and muted colors. Jupiter's atmosphere contains ammonia in addition to hydrogen and helium. And in certain altitude ranges and temperature zones, the ammonia combines with water to form slushy hailstones. These mushballs, as scientists call them, form in the turbulent regions where ammonia gas mixes with water clouds, freezing together into aggregates that can grow quite large. The mushballs contain a mixture of ammonia and water ice in a ratio that keeps them slushy rather than solid. And this slush is dense enough to fall deeper into the atmosphere rather than being held aloft by updrafts. As they fall, they carry ammonia from the upper atmosphere down to deeper levels, removing it from the regions where spacecraft can detect it. This process helps explain observations that puzzled scientists for years. Measurements showing less ammonia in certain atmospheric layers than models predicted. The ammonia was not missing, but rather locked up in mushballs that had fallen into deeper, warmer regions, where they eventually evaporate and release the ammonia back into the gas phase. The discovery of this process required observations from the Juno spacecraft, which measured the atmosphere's composition at different depths and found the depletion patterns that suggested ammonia was being transported downward by precipitation. The mushballs themselves cannot be directly observed because they form in cloud layers too deep and turbulent for cameras to see clearly. But their effects on atmospheric composition reveal their presence. The hailstones form at temperatures between -100 and -150 degrees Fahrenheit, where ammonia hydrate ice becomes stable. They grow as they fall, collecting more ammonia and water from the surrounding clouds, potentially reaching sizes of several centimeters across, before descending into warmer regions, where they begin to evaporate. The process creates a continuous cycle of ammonia, moving up and down through the atmospheric layers, driven by condensation, precipitation, and evaporation, a pattern fundamentally similar to water's behavior on Earth, despite the vastly different temperatures and pressures involved. Mars presents one of the solar system's most beautiful atmospheric phenomena, a sunset that reverses the colors seen from Earth. On Earth, the setting sun appears yellow or orange or red, while the sky around it glows in shades of orange and pink and red, the colors created by sunlight scattering through air molecules and dust particles. On Mars, the sun itself appears bluish-white or pale blue when near the horizon, while the sky around it glows in shades of butterscotch and pink and tan. This color reversal happens because of the fine dust suspended in Mars's thin atmosphere, particles that scatter light differently than Earth's air molecules. The Martian dust particles are larger than the molecules that dominate Earth's atmosphere, and they preferentially scatter red and yellow light, removing it from the direct sunlight path and spreading it across the sky. Blue light, being less affected by the dust, continues in a straighter path and reaches your eyes more directly when you look at the sun itself. The result is a sun that appears bluish when surrounded by dusty atmosphere, and a sky that glows warm colors. The effect is most pronounced when the sun is near the horizon and its light passes through the maximum amount of dust-laden atmosphere, exactly when Earth's sunsets show their most vivid colors too. But with the colors inverted, the Martian sky color changes depending on how much dust is suspended in the air, which varies with season and with dust storm activity. During major dust storms that occasionally envelop the entire planet, the sky becomes much lighter, almost salmon pink even at noon, and the sun nearly disappears behind the thick dust. During calm periods with clear air, the sky appears darker, more butterscotch than pink, and the sun's blue tint becomes more subtle. The seasonal variation in atmospheric dust creates a constantly changing sky appearance, with some times of year showing more vivid colors and others presenting more muted tones. Uranus appears nearly featureless when viewed in visible light, its pale cyan color showing almost no variation across its disk. This bland appearance puzzled astronomers for years, suggesting either a very uniform atmosphere or some mechanism that prevents deeper clouds from being visible. The answer involves methane in the upper atmosphere, which absorbs red light efficiently and gives the planet its cyan color. Above this methane-rich layer sits a thick haze layer that acts like a cap, preventing deeper atmospheric features from showing through. The haze consists of tiny particles suspended at high altitude, possibly photochemical products created when ultraviolet light interacts with methane molecules. This haze layer makes Uranus appear much more uniform than Neptune, which has a similar atmospheric composition, but a clearer upper atmosphere. When astronomers observe Uranus in specific infrared wavelengths that can penetrate the haze layer, they detect cloud features and atmospheric bands that are invisible in normal light. The planet's atmosphere contains the same kinds of structures seen on other giant planets, including convection cells, wind bands, and storm systems, but all hidden beneath the haze cap. The difference between Uranus and Neptune's appearance, despite their similar composition, suggests that subtle differences in atmospheric chemistry or temperature profiles can create dramatically different visibility conditions. The mystery of why Uranus has this thick haze cap, while Neptune does not, remains unsolved, with various hypotheses suggesting different atmospheric circulation patterns, temperature differences, or chemical processing rates. Understanding this difference would help scientists better model the atmospheric chemistry of not just these two planets, but also similar ice giant planets that likely exist around other stars. The haze demonstrates that appearances can be deceiving, with Uranus looking calm and uniform while actually possessing complex atmospheric dynamics hidden just below the visible surface. Saturn's North Pole hosts one of the solar system's most geometrically remarkable features, a hexagonal jet stream pattern that extends hundreds of miles deep into the atmosphere. Each side of the hexagon measures approximately 9,000 miles, making the overall structure larger than Earth's diameter. The hexagon was first glimpsed by Voyager spacecraft in the 1980s and has been continuously observed by Cassini from 2004 to 2017. Revealing that the structure persists for decades, with its basic shape remaining stable, despite being composed of flowing gas. The hexagon rotates with the same period as Saturn's interior rotation, suggesting it is somehow anchored to the deeper atmospheric layers. The mechanism that creates and maintains such a precisely six-sided structure in a fluid like an atmosphere remains somewhat mysterious, though laboratory experiments have reproduced similar patterns in rotating fluids with specific combinations of rotation rates and flow speeds. The hexagon appears to be a standing wave pattern in the jet stream, with 6 wave peaks and 6 wave troughs arranged around the pole. The wave remains stationary relative to Saturn's interior rotation, while the winds within it blow at speeds exceeding 200 miles per hour, circling the pole in about 10.5 hours. Inside the hexagon sits a massive storm system at the exact North Pole, suggesting some connection between the polar vortex and the hexagonal jet stream pattern. The hexagon changes color with Saturn's seasons, appearing golden during northern winter and shifting toward bluer hues as northern summer approaches. Changes possibly related to the amount of sunlight reaching the North Pole and affecting the atmospheric chemistry. The seasonal shift in color suggests that photochemical processes alter the composition of the haze particles in the hexagon, creating different scattering properties. The hexagon has no counterpart at Saturn's south pole, which instead shows a more typical circular polar vortex, adding to the mystery of what specific conditions create the northern hexagonal pattern. Earth's atmosphere, when viewed from space, displays a phenomenon invisible from the ground, a faint green glow in a thin layer approximately 100 kilometers above the surface. This airglow comes from oxygen molecules that absorb ultraviolet light from the sun during the day, becoming energized, and then release that energy as visible green light at night. The emission creates a layer of faint glow surrounding the planet, visible to astronauts on the International Space Station looking toward the horizon, where the airglow layer appears as a thin green line separating the black of space from the darker bulk of the Earth below. The airglow is far too faint to be noticed from the ground looking up, because we view it through all the atmosphere below it, which scatters so much light that the airglow is lost in the general sky brightness. From space, looking at the edge of the atmosphere, the viewing geometry enhances the visibility of the thin, glowing layer, allowing it to be photographed and studied. The intensity varies with solar activity, becoming brighter when the sun is more active and sending more ultraviolet radiation toward Earth. The airglow also varies with latitude and season, creating patterns that reveal how atmospheric circulation moves oxygen and other gases around the upper atmosphere. The green glow represents energy from the sun being temporarily stored in oxygen molecules and then slowly released, a process that happens continuously in the thin upper reaches of our protective atmosphere. The phenomenon connects to similar processes on other planets, where different atmospheric gases create different colors of airglow, though Earth's oxygen-rich atmosphere creates a uniquely green signature. The airglow serves as a visible reminder that the atmosphere is not passive, but actively interacts with solar radiation, absorbing energy and re-emitting it in ways that shape the upper atmospheric chemistry. And these strange skies, with their inverted colors and sustained storms and geometric patterns, all depend partly on what lies beneath them. And when we look at where water exists across the solar system, we find it in forms and places that range from the familiar to the utterly unexpected. Water, the molecule that defines habitability as we understand it, appears throughout the solar system in frozen, liquid, and vapor forms, hidden beneath surfaces, or locked in polar ice, or suspended in atmospheres. The distribution of water across different worlds tells the story of how the solar system formed and how conditions in each location determined what happened to the water that was present. Some worlds hold water in quantities that dwarf Earth's oceans, while others preserve tiny amounts in permanently shadowed craters. And the forms water takes reveal the temperature, pressure, and geological history of each location. Jupiter's moon Europa, slightly smaller than Earth's moon, possesses a surface of water ice that appears remarkably smooth compared to most cratered moons. Beneath this ice shell, evidence suggests a global ocean exists, containing liquid water in contact with a rocky seafloor. The evidence comes from multiple sources, including magnetic field measurements that detected induced fields consistent with a salty conducting layer beneath the surface. The surface features themselves, including patterns of cracks and ridges, and regions where the ice appears to have broken and refrozen, suggest that the ice floats on something fluid rather than sitting on solid rock. The ice shell's thickness remains uncertain, with estimates ranging from 15 to 25 kilometers in the thinnest regions. Below this frozen crust, the ocean may extend to depths of 100 kilometers or more, holding twice as much water as all of Earth's oceans combined, despite Europa being only 1/4 Earth's diameter. The ocean stays liquid despite the intense cold at Jupiter's distance from the Sun, because tidal heating from Jupiter's gravity flexes Europa continuously as it orbits. This flexing generates friction in the Moon's interior, producing enough heat to keep a vast reservoir of water in liquid form. Within the ice shell itself, scientists have identified features that suggest pockets of liquid water may exist suspended in the ice, floating above the main ocean like lakes within a glacier. These pockets would form when warmer ice rises from below through convection and partially melts, creating lenses of liquid surrounded by solid ice. The liquid would be denser than pure water because of dissolved salts and other materials, and it might persist for thousands or millions of years before freezing completely. The existence of these suspended water pockets could explain some surface features where the ice appears to have collapsed, or where material from beneath has reached the surface without requiring the ice shell to be very thin everywhere. Mars, now a cold desert with a thin atmosphere that cannot support liquid water at the surface for long, holds substantial quantities of water, frozen in various locations. The polar ice caps, visible in small telescopes from Earth, consist of layered water ice and carbon dioxide ice, with the permanent caps remaining throughout the Martian year, while seasonal caps grow and shrink with the changing temperature. Beneath the North Polar Cap, radar soundings have revealed layers of ice and dust, extending several kilometers deep, representing a climate record that preserves information about Martian conditions over millions of years. In the mid-latitudes, buried beneath a thin layer of soil and dust, lies a massive deposit of water ice extending across an area the size of New Mexico. This buried glacier, discovered by radar that penetrated the surface, holds as much water as Lake Superior and sits at depths ranging from 1 to 10 meters below the surface. The ice accumulated during different climate conditions on Mars, when the planet's axial tilt was different and ice could form at lower latitudes than it can today. The deposit remains stable now, protected from sublimation by the overlying dirt layer that insulates it from the atmosphere and sunlight. The discovery of this buried ice changed calculations about how much accessible water exists on Mars and where future human missions might be able to extract it. Water ice at shallow depths could be reached by simple digging rather than requiring deep drilling or complex extraction from polar regions. The ice's purity varies throughout the deposit, with some regions showing nearly pure ice, while others contain significant amounts of dust and rock mixed with the frozen water. The variation reflects the conditions under which the ice accumulated, with purer ice forming during periods of direct precipitation and dustier ice forming when airborne dust settled onto existing ice deposits. The dwarf planet Ceres, largest object in the asteroid belt between Mars and Jupiter, surprised scientists with evidence of recent water activity, despite its small size and distance from the Sun. When the Dawn spacecraft observed Ceres up close, it found bright spots in several craters that turned out to be deposits of salt left behind when briny water reached the surface and evaporated. The brightest spots sit in Okatir crater, where a central dome made of salt minerals rises from the crater floor, surrounded by smaller salt deposits scattered across the crater's interior. The salts indicate that liquid briny water existed beneath Ceres' surface recently, perhaps within the last few million years, and possibly still exists in some regions. The water would be salty enough to remain liquid at temperatures where pure water would freeze, similar to how salt on Earth's roads prevents ice from forming at temperatures slightly below freezing. Ceres may possess pockets of briny water at depths of several kilometers, kept liquid by the small amount of heat generated by radioactive decay in the rocky core or by lingering heat from the dwarf planet's formation. When fractures allowed this brine to reach the low-pressure environment near the surface, the water evaporated quickly, leaving concentrated salt deposits behind. The discovery of these salt deposits and the evidence for recent or even ongoing brine activity made Ceres one of the potentially interesting locations for studying chemistry in liquid water beyond Earth. The brine composition includes sodium carbonate and ammonium chloride, among other compounds, creating a chemical environment different from Earth's oceans or the suspected oceans inside icy moons. The persistence of this activity on a body as small and seemingly inactive as Ceres suggests that liquid water may exist in more locations throughout the solar system than previously thought, wherever local conditions of composition and heat preservation allow it. Saturn constantly gains water from its ring system through a process called ring rain, where water ice particles from the rings spiral inward and fall into the planet's upper atmosphere. The rings sit within the region where Saturn's magnetic field rotates with the planet, and this rotation creates forces that gradually remove the smallest particles from the rings. These tiny particles, electrically charged by ultraviolet light and interactions with Saturn's magnetic field, spiral along magnetic field lines toward the planet's equator, where they enter the atmosphere and vaporize. The process deposits between 400 and 2,800 kilograms of water ice into Saturn's atmosphere every single second. This continuous rain affects Saturn's atmospheric chemistry in the upper layers, adding water to regions that would otherwise be very dry, because water freezes at the cold temperatures of the upper atmosphere and sinks to lower, warmer levels. The ring rain creates a band of enhanced water content in the upper atmosphere at equatorial latitudes, detectable through spectroscopic observations. The process also means the rings are gradually being depleted, losing mass to ring rain, as well as to other processes, like micrometeorite bombardment, that knock particles out of the rings entirely. Current estimates suggest the rings may last only another 100 to 300 million years before losing enough mass to become much thinner or possibly disappearing entirely. The rate of ring rain varies with Saturn's seasons because the ring particles' interactions with sunlight change as the angle of illumination shifts. During equinox, when the sun shines directly edge-on to the rings, the rain rate differs from during solstice, when the sun illuminates one face of the rings more strongly. These seasonal variations affect how quickly different parts of the rings lose mass and may influence which regions deplete fastest. The ring rain demonstrates that even structures that appear stable are constantly evolving, gradually changing over timescales long compared to human experience. but brief in astronomical terms. Earth's moon, seemingly dry and airless, holds water ice in permanently shadowed craters at both poles. These craters never receive direct sunlight because of the moon's very small axial tilt, creating cold traps where temperatures remain below -230 degrees Fahrenheit year-round. Any water molecule that enters these craters by chance becomes frozen to the surface immediately and remains there, unable to escape because the temperature never rises enough to cause sublimation. Over billions of years, water from various sources has accumulated in these dark refuges. The water originates from multiple sources, including comet impacts that deliver water ice directly, solar wind hydrogen that combines with oxygen in lunar minerals to form water, and possibly primordial water trapped during the moon's formation. Measurements from orbiting spacecraft using different techniques have confirmed the presence of water ice in multiple shadowed craters, with the highest concentrations appearing in the coldest areas that have remained dark for the longest time. The total amount of ice remains uncertain, but estimates suggest millions of tons exist, scattered across dozens of permanently shadowed regions. Some of these deposits may be billions of years old, meaning the ice has been frozen in complete darkness for longer than complex life has existed on Earth. The ice is mixed with lunar soil rather than forming pure deposits, with the concentration varying from a few percent to possibly 30% water ice in the richest areas. Extracting this water would require excavating the ice-bearing soil and heating it to drive off the water vapor, which could then be collected and condensed. Future lunar bases might use this polar water ice as a resource, breaking it down into hydrogen and oxygen for rocket fuel, or simply using it for life support and drinking water. Jupiter's moon Ganymede, the largest moon in the solar system, possesses a more complex water structure than any other known world. Beneath its ice shell sits not one, but multiple layers of liquid ocean, separated by layers of high-pressure ice that forms when the immense weight of overlying material compresses water into crystal, structures that are denser than liquid water. The result resembles a club sandwich, with alternating layers of liquid water and exotic ice extending deep into Ganymede's interior. The layering occurs because the pressure increases with depth, and at certain pressure thresholds, water transitions from liquid to high-pressure ice phases that remain solid even at temperatures above the normal freezing point. The uppermost ocean sits beneath a crust of normal ice similar to Europa's configuration, though Ganymede's ice shell is likely thicker, possibly 90 to 150 kilometers. Below this ocean lies a layer of ice 5, a high-pressure ice form that is denser than water, and below that, another liquid ocean, followed by another ice layer of a different high-pressure form. The structure may include several such alternating layers before reaching the rocky seafloor at Ganymede's center. Each ocean layer remains isolated from the others by the ice barriers, creating separate water environments that have not mixed for billions of years. This complex structure means Ganymede contains more liquid water than any other solar system body, possibly exceeding even Earth's ocean volume by a substantial margin. However, the water is distributed across multiple separate oceans at different depths and pressures rather than forming one continuous body. The chemistry and temperature in each layer would differ, with deeper layers experiencing higher pressures and possibly different dissolved mineral contents. Whether life could exist in such isolated high-pressure environments remains entirely speculative. But the existence of these stacked oceans demonstrates that water's behavior under different pressure regimes creates configurations impossible on Earth, where our ocean experiences relatively modest pressure variation. Mercury, the closest planet to the Sun with daytime temperatures reaching 800 degrees Fahrenheit, possesses water ice at its poles in circumstances similar to the Moon's polar ice. Despite the extreme heat during Mercury's long day, craters at the poles remain permanently shadowed because of Mercury's very small axial tilt. The floors of these craters never receive direct sunlight, creating cold traps where temperatures plunge to perhaps -300 degrees. Radar observations from Earth detected bright reflections from these shadowed crater floors consistent with water ice, a finding confirmed when the Messenger spacecraft observed the regions and found the bright deposits right where the permanently shadowed areas sit. The presence of water ice so close to the Sun seems paradoxical, but the extreme conditions at Mercury create the possibility for such contrasts. Areas just a few feet outside the permanently shadowed craters bake in sunlight hot enough to melt lead, while the crater floors a short distance away remain frozen at temperatures cold enough to preserve water ice for billions of years. The ice likely accumulated from comet impacts over Mercury's history, with water from the impacts becoming distributed across the surface and eventually migrating to the cold traps where it became permanently frozen. Some shadowed craters also show evidence for organic compounds mixed with the ice, delivered by the same cometary impacts that brought the water. These ice deposits represent the coldest locations in the inner solar system, colder than anywhere on Venus, Earth, Mars, or the Moon despite Mercury's proximity to the Sun. The paradox illustrates how local geometry and conditions matter more than average temperature when determining where ice can survive. The permanently shadowed craters create microenvironments completely isolated from the surrounding heat, preserving conditions that existed when the ice arrived. The deposits will remain frozen as long as Mercury's orbital and rotational configuration keeps those craters shadowed, a situation that will persist for billions of years into the future. Mars shows clear evidence that liquid water once flowed across its surface in quantities sufficient to carve valleys, form lakes, and possibly create an ocean covering much of the northern hemisphere. The smooth northern plains sit several kilometers lower in elevation than the southern highlands, and the boundary between them shows features consistent with an ancient shoreline. Terraces, sediment deposits, and valley networks that would have drained into the northern lowlands all suggest that a body of standing water once filled the depression. The estimated size of this ancient ocean varies depending on how the evidence is interpreted, but it may have covered a third of the planet's surface and held a volume of water comparable to Earth's Arctic Ocean. The age of this ocean remains uncertain, with most evidence suggesting it existed more than 3 billion years ago, during a period when Mars had a thicker atmosphere and warmer climate than today. The water would have been in contact with the atmosphere, undergoing evaporation and precipitation, with rivers draining into it from the surrounding highlands. Over time, as Mars lost much of its atmosphere to space and the climate cooled, the ocean would have gradually frozen and then sublimated, with the water vapor either being lost to space or migrating to the poles, where it froze into the ice caps. The minerals left behind by the evaporating ocean may still exist in the northern plains, buried beneath the volcanic flows and wind-blown dust that have covered the surface in the billions of years since the ocean disappeared. The debate over Mars's ancient ocean continues, with some researchers interpreting the evidence as supporting a large body of standing water, while others suggest the features could have formed through other processes. The shoreline features are degraded by billions of years of impacts, volcanism, and erosion, making them difficult to identify conclusively. The discovery of clay minerals and other water-altered rocks in the region surrounding the proposed ocean strengthens the case that water existed there, though whether it formed a true ocean or merely a series of large lakes remains uncertain. The evidence collectively points toward a Mars that was once much wetter than today, with water playing a major role in shaping the landscape before climate changes transformed it into the cold desert we observe now. And this water, in all its varied forms and locations, has shaped many worlds, but fire shapes them too. And volcanic activity appears in forms far stranger than anything erupting on Earth, with ice volcanoes and sulfur geysers creating landscapes that redefine what volcanism means. Volcanic activity, the process by which material from a world's interior reaches its surface, takes forms across the solar system that expand the concept far beyond molten rock, erupting from cracks in the ground. On some worlds, the erupting material is water or ammonia rather than silicate lava, while on others, the chemistry and temperature create lavas with properties utterly different from Earth's basaltic flows. These eruptions, whether hot or cold, violent or gentle, constantly reshape surfaces and reveal what lies beneath. Jupiter's moon Io experiences the most intense volcanic activity of any body in the solar system, with eruptions occurring constantly from hundreds of active vents scattered across its surface. The volcanic material consists mostly of sulfur compounds and silicate lava, both types erupting from different vents, sometimes mere kilometers apart. The most spectacular eruptions shoot material more than 200 miles above the surface, creating volcanic plumes visible from spacecraft orbiting Jupiter. One volcano, Prometheus, has been continuously active since Voyager spacecraft first observed it in 1979, erupting without pause for more than 4 decades. The lava on Io reaches temperatures that exceed 1600 degrees Celsius in some locations, hotter than any current volcanic eruption on Earth. These extremely high temperatures suggest the lava has a composition richer in magnesium than typical Earth basalts, possibly resembling ultramafic lavas that erupted on Earth billions of years ago when the planet's interior was hotter. The high temperatures also allow the lava to flow more easily, spreading across Io's surface in thin sheets that cover older features rapidly. This continuous resurfacing erases impact craters almost as quickly as they form, giving Io the youngest surface in the solar system, with an average age of only a few million years in most regions. Some of Io's volcanic centers contain lava lakes, calderas filled with molten rock that constantly churns and overturns. The largest known lava lake, Loki Patera, covers about 10,000 square miles and appears to undergo periodic overturning events where the entire surface crust of the lake founders and sinks, allowing fresh, hot lava to well up from below. These overturning events occur roughly every 400 to 600 days, creating brightening, visible, in infrared observations from Earth-based telescopes and spacecraft. The scale of Loki Patera dwarfs any lava lake on Earth, holding more molten rock than all of Earth's currently active lava lakes combined. The energy driving Io's volcanism comes entirely from tidal heating, the same process that keeps Europa's ocean liquid, but operating far more intensely. Io's orbit is slightly elliptical due to gravitational interactions with Europa and Ganymede, causing Io's distance from Jupiter to vary as it orbits. This variation changes the strength of Jupiter's tidal pull on Io, flexing the moon's interior and generating friction that melts rock deep within. The heat generated exceeds the heat Earth produces from radioactive decay by a factor of about 200 times per unit mass, making Io's interior far more active than Earth's, despite being only slightly larger than our moon. Saturn's moon Enceladus releases water rather than molten rock, with geysers erupting from the tiger stripe fractures at the South Pole. More than 100 distinct geysers have been identified, each erupting continuously, though the intensity varies with Enceladus's orbital position around Saturn. The geysers shoot water vapor, ice crystals, salt particles, silica particles, and organic molecules into space at speeds exceeding 800 miles per hour. The fastest moving material escapes Enceladus's weak gravity entirely and enters orbit around Saturn, where it forms the diffuse E-ring, a broad torus of tiny ice particles that extends from inside Enceladus's orbit all the way out beyond Rhea's orbit. The water erupting from Enceladus comes from the global ocean beneath the ice shell, pressurized by the weight of the overlying ice and heated by tidal flexing from Saturn's gravity. The tiger stripes represent fractures where the ice has been pulled apart by tidal stresses, creating openings through which the pressurized water can escape. As the water travels upward through the fractures, the decreasing pressure causes dissolved gases to come out of solution, similar to how opening a soda bottle releases carbon dioxide. The expanding gases help propel the water upward and out through the vents at the surface, where the sudden drop to vacuum causes instant freezing, creating the plumes of ice particles and vapor. Analysis of the plume material has revealed surprising details about the ocean's chemistry. The presence of salt indicates the ocean is in contact with rock, rather than sitting between ice layers, allowing chemical exchange between water and minerals. The detection of silica particles suggests hydrothermal activity may be occurring at the ocean floor, with hot water dissolving silica from rocks and then carrying it upward. Such hydrothermal systems on Earth support ecosystems that don't rely on sunlight, making the possibility of similar chemistry on Enceladus scientifically interesting. The organic molecules detected in the plumes include some with carbon-hydrogen bonds, though none complex enough to be considered definitive biosignatures. Neptune's moon Triton, despite being even colder than Enceladus, with surface temperatures around -390 degrees Fahrenheit, displays active eruptions of nitrogen gas. These geysers occur in the southern hemisphere during summer, when the sun's faint warmth slightly warms the surface. Beneath the visible surface lies a layer of transparent nitrogen ice, and beneath that, a layer of darker material that absorbs sunlight more efficiently. Sunlight penetrating through the transparent ice layer heats the darker layer beneath, causing nitrogen ice at that depth to vaporize, and build up pressure. When the pressure becomes strong enough, it breaks through the overlying ice and erupts as a geyser. The nitrogen gas shoots upward 8 kilometers or more, carrying dark particles with it from the subsurface layer. The gas then spreads out horizontally in the thin atmosphere, and the dark particles settle gradually onto the surface downwind of the eruption site. This process creates dark streaks across Triton's pink nitrogen ice plains, all aligned in the same direction determined by the prevailing wind patterns. The streaks extend for up to 100 miles from each active geyser, marking the deposition pattern of erupted material. Multiple geysers, active simultaneously, create a pattern of parallel dark streaks, visible in Voyager 2 images from 1989. The geysers are seasonal phenomena, occurring only when that region of Triton receives continuous sunlight during the southern summer. During winter, temperatures drop low enough that nitrogen remains completely frozen and no pressure builds up. The seasonal nature means the dark streaks observed in 1989 have likely faded or been buried by fresh nitrogen frost during the decades since, and new streaks are forming in currently active regions. The discovery of these nitrogen geysers expanded the definition of volcanic activity to include gas-driven eruptions powered by solar heating rather than internal heat, showing that eruption mechanisms are even more diverse than previously recognized. Venus potentially harbors active volcanism today, though proving this has been difficult because the thick clouds prevent direct observation of the surface. Some evidence comes from variations in sulfur dioxide levels in the atmosphere, measured over several years, with increases suggesting fresh volcanic eruptions releasing new gas. Other evidence includes infrared hotspots detected by the Venus Express spacecraft, showing regions of the surface slightly warmer than their surroundings, possibly indicating recent lava flows that have not yet cooled to ambient temperature. The strongest evidence comes from radar images taken by the Magellan mission, showing features that appear to be volcanic and comparing them to radar images taken decades earlier by earlier missions, revealing changes in brightness that could indicate fresh lava flows. The uncertainty arises because the evidence is indirect, relying on remote sensing data that could be explained by other processes. Sulfur dioxide variations might result from atmospheric circulation changes, rather than new eruptions. Infrared hotspots could be caused by compositional differences in surface minerals, rather than residual heat from lava. And radar brightness changes might have other explanations. Definitive proof of current volcanic activity would require either landing on an active volcano or observing an eruption directly, neither of which has yet been accomplished. Current plans for future Venus missions include long-lived surface stations and orbital radar capable of higher resolution than Magellan achieved. Observations that might resolve the question: if Venus is currently volcanically active, the eruptions would be silicate lava similar to Earth's, though occurring in an environment utterly unlike any volcanic setting on Earth. The atmospheric pressure at the surface is 90 times Earth's sea level pressure, which would affect how lava flows and how volcanic gases behave. The extreme heat means that lava would remain molten longer than on Earth, spreading farther before solidifying, and volcanic gases would not rise as easily through the dense atmosphere. The combination of extreme conditions makes Venus a natural laboratory for understanding how volcanism operates under circumstances never encountered on Earth, though actually observing the processes remains frustratingly difficult from orbit. Mars hosts Olympus Mons, the solar system's largest volcano, a shield volcano so massive it dwarfs anything Earth has produced. The volcano stands about 22 kilometers high, measured from the surrounding plain to the summit caldera, making it nearly 3 times the height of Mount Everest, above sea level. The height alone is impressive, but the sheer size of the structure becomes even more remarkable when considering the base diameter, which spans roughly 600 kilometers, about the same as the state of Arizona. The slopes are generally gentle, averaging only about 5 degrees, but the edges feature cliffs that rise up to 8 kilometers in some locations. These boundary cliffs likely formed as the volcano grew and spread outward, with the edges collapsing under their own weight to create the escarpment. Standing at the base of one of these cliffs would present a vertical wall rising 5 miles straight up, a sheer face taller than Mount Everest, measured from sea level to summit. The cliff face would disappear into the thin Martian atmosphere above, and no climbing route could exist on such a vertical expanse. From the top of the cliff, looking down, the base would lie so far below that atmospheric haze might obscure it entirely, creating the impression of standing at the edge of the world. The volcano last erupted perhaps as recently as 25 million years ago, though the exact age of the youngest flows remains uncertain. Compared to Earth's timescales, this seems ancient, but geologically it represents relatively recent activity, suggesting the volcano might not be permanently extinct. Future eruptions remain possible if Mars's interior still retains enough heat to generate magma, though the planet's cooling over billions of years makes renewed activity increasingly unlikely. The lack of erosion on Mars means the volcanic features remain pristine, showing details that would be smoothed away by water and wind on Earth within thousands of years. Uranus's moon Ariel displays evidence of cryovolcanic activity, eruptions of water or water-ammonia mixtures that occurred relatively recently in geological terms. The surface shows vast, smooth plains with few impact craters, indicating something has resurfaced portions of the moon within perhaps the last few 100 million years. Long, sinuous valleys cut across the surface, resembling channels carved by flowing liquid or created when subsurface liquid drained away, causing the overlying crust to collapse. Some regions show what appear to be flow features, bright material that emerged from fractures and spread across older terrain before freezing solid. The cryovolcanic material probably consisted of water, mixed with ammonia or methane, compounds that lower the freezing point and allow the mixture to remain liquid at temperatures where pure water would be frozen solid. At Ariel's distance from the Sun and its small size, surface temperatures sit around -170 degrees Celsius, far too cold for pure water to flow. A water-ammonia mixture, however, can remain liquid down to around -100 degrees Celsius, depending on the concentration, allowing it to erupt and flow despite the extreme cold. Once exposed to the surface environment, the liquid would freeze relatively quickly, but perhaps not before flowing for some distance and creating the features visible today. The energy source for Ariel's cryovolcanism remains somewhat mysterious given the moon's small size and great distance from the Sun. Tidal heating seems the most likely explanation, though Ariel's current orbit is nearly circular and should not produce significant tidal flexing. The moon may have been in a resonant orbit in the past, that pumped tidal energy into its interior, heating it enough to drive volcanic activity. And the evidence we see today represents the aftermath of that active period. Alternatively, heat from radioactive decay of elements in Ariel's rocky core might have provided enough energy, though this seems less likely given the Moon's modest size of about 1,200 kilometers in diameter. Earth's own volcanic activity may have been influenced by the Moon early in our planet's history, when the Moon orbited much closer than today. Shortly after the giant impact that formed the Moon about 4.5 billion years ago, the Moon sat only about 15,000 miles from Earth, compared to the current 240,000 miles. At that distance, tidal forces would have been hundreds of times stronger than today, flexing Earth's interior and generating enormous amounts of heat through friction. This tidal heating would have supplemented the heat from radioactive decay and from the residual warmth of Earth's formation, potentially driving more intense volcanic activity than would have occurred from those sources alone. As the Moon gradually receded over hundreds of millions of years, the tidal heating decreased, and Earth's volcanic activity became driven primarily by internal heat sources. The effect was probably most significant during the first billion years of Earth's history, a time when volcanic activity was already intense due to the young planet's hotter interior. Evidence for this early volcanic intensity comes from the composition of ancient rocks and from the rapid formation of Earth's early crust, processes that required extensive volcanic activity to move material from the interior to the surface. The Moon's influence thus contributed to shaping Earth's early geological evolution, though disentangling its specific contribution from other heat sources remains challenging. The dwarf planet Ceres hosts a volcanic mountain named Olympus Mons that appears to be a cryovolcano, a dome of ice mixed with salts and other materials that erupted and piled up rather than flowing far from the vent. The mountain rises about 4 kilometers above the surrounding plain and spans about 17 kilometers at its base, making it prominent in images of Ceres's surface. The slopes show bright streaks of material that may represent salt deposits left behind when briny water ice erupted and then sublimated, leaving the dissolved minerals behind. The mountain's shape and structure differ from impact crater peaks or other features, strongly suggesting a volcanic origin. Dating, based on crater counts, indicates Olympus Mons may be only about 200 million years old, extremely young compared to most of Ceres's surface, which shows billions of years of accumulated impact craters. This young age suggests Ceres may have experienced cryovolcanic eruptions relatively recently, possibly even remaining active today, though no current eruptions have been detected. The composition of the erupted material probably included water ice, ammoniated clay minerals, carbonates, and salts. A muddy ice mixture quite different from molten rock, but capable of flowing and building structures when pressurized and heated slightly. The heat source for Ceres's cryovolcanism likely comes from radioactive decay in the rocky component of its interior, possibly concentrated in local pockets that accumulated enough heat to melt ice and create subsurface reservoirs of briny liquid. When pressure built up sufficiently, the liquid could breach the overlying crust and erupt at the surface, building the dome we see as Olympus Mons. The fact that only one prominent cryovolcanic dome exists suggests the activity is rare and sporadic, with long dormant periods between eruptions. Other smaller domes might exist, but have been degraded by impacts or obscured by later deposits, making Olympus Mons the most obvious survivor of Ceres' limited cryovolcanic history. These volcanic worlds, from the sulfur-painted landscape of Io to the icy geysers of Enceladus to the nitrogen fountains of Triton, demonstrate that volcanic activity takes countless forms depending on a world's composition, temperature, and energy sources. The variety expands our understanding of how interiors connect to surfaces, how heat escapes from planetary bodies, and how the simple process of eruption can create landscapes that range from the familiar to the utterly alien. And among all the worlds shaped by eruptions, the moons themselves stand out for characteristics that go far beyond volcanic activity. The dozens of moons orbiting the giant planets display characteristics so unusual that they challenge assumptions about what moons can be, with features that range from orbital oddities to surface textures to structural properties that have no parallels on the terrestrial planets. These characteristics emerged from formation processes, tidal interactions, impacts, and other events that shaped each moon's unique identity. Some moons appear almost ordinary until close examination reveals something deeply strange, while others announce their peculiarity from the first glimpse. Miranda, the smallest of Uranus's 5 major moons, displays a surface that looks as though someone took 3 or 4 different moons and assembled them incorrectly into one body. The surface divides into distinct regions with completely different terrain types that meet at sharp boundaries rather than blending gradually together. One region shows heavily cratered ancient terrain, dark and battered by billions of years of impacts. Adjacent to this sits a region of parallel ridges and valleys creating a grooved or streaked appearance, the grooves running in one direction as if the surface was stretched and broken. Nearby appears a region of bright, lightly cratered terrain, covered in chevron-shaped features, V patterns that point in consistent directions. The boundaries between these terrains appear unnaturally abrupt, as if each section came from somewhere else and was placed next to the others without any transition zone. The formations creating this patchwork pattern remain somewhat mysterious, though the most widely accepted explanation involves tidal heating events in Miranda's past that partially melted the interior, allowing denser material to sink and lighter material to rise. This differentiation would have brought different materials to the surface in different regions, creating the distinct terrain types. Subsequent cooling and solidification froze these regions in place, preserving the boundaries we see today. Miranda also hosts Verona Rupes, a cliff face that rises approximately 20 kilometers from base to top, making it the tallest known cliff in the solar system. The cliff formed when a section of Miranda's crust faulted and dropped relative to the adjacent section, creating a vertical escarpment that dwarfs anything on Earth. Dropping a stone off the top of Verona Rupes would take about 12 minutes to hit the bottom due to Miranda's weak gravity, only about 1% of Earth's. A person jumping off the cliff would experience the same long fall, though at Miranda's escape velocity of only about 200 meters per second, jumping with sufficient force could potentially escape the moon's gravity entirely. From the base of Verona Rupes looking upward, the cliff face would rise beyond visibility, disappearing into the black sky above, its full height impossible to appreciate from the ground level. From the top looking down, the base would lie so far below that the curvature of Miranda's small surface might make the distant ground appear to curve away. The cliff face itself would show layering in Miranda's crust, different compositions and densities visible as distinct strata, each layer representing a different episode in the moon's formation or evolution. No analog exists on Earth for such a massive cliff on such a small world, making Verona Rupes unique in the solar system. Saturn's moon Hyperion presents a different kind of strangeness, appearing in images like a sponge or a piece of cosmic foam rather than a solid body. The surface is covered in deep craters that have not filled in or softened over time, instead remaining as steep-walled pits that give the moon its porous appearance. The overall shape is irregular, roughly potato-like, measuring about 360 by 280 by 220 kilometers along its three axes. The density of Hyperion measures only about half that of water ice, suggesting the interior is not solid, but rather contains vast amounts of empty space, possibly a rubble pile structure with gaps between individual chunks. The craters show unusual characteristics compared to impact craters on most other moons, with dark material coating their floors and walls, while brighter ice appears on the edges and in between craters. This pattern suggests the darker material lies beneath a thin layer of bright ice, and impacts punch through the bright surface to expose the dark layer below. Alternatively, the dark material might be coating that accumulates on surfaces exposed to space, while bright ice remains on edges and ridges. The sponge-like appearance combined with the low density suggests Hyperion might be composed of loosely aggregated material that never compressed into a solid body, allowing impacts to punch out cavities rather than creating typical bowl-shaped craters. Hyperion also exhibits chaotic rotation, tumbling irregularly rather than rotating with a fixed period, like most moons. The irregular shape and the gravitational influence of nearby Titan create torques that prevent Hyperion from settling into synchronous rotation, as most large moons do. Instead, Hyperion tumbles unpredictably, with its orientation changing in complex ways that would be impossible to predict far in advance. Standing on Hyperion's surface, you would see Saturn moving through the sky in an irregular pattern, sometimes rising and setting quickly, other times moving slowly or remaining in one general area for extended periods, the movement depending on Hyperion's current tumbling motion. Mars's moon Phobos orbits so close to the planet that tidal forces are gradually pulling it inward, dooming it to either crash into Mars or break apart into a ring system within the next 30 to 50 million years. Phobos currently orbits at about 9,300 kilometers from Mars's center, well inside the classical Roche limit for a rigid body. Though Phobos' internal strength allows it to hold together for now, the orbit decays by about 2 centimeters per year, an imperceptibly small amount in human terms, but significant over geological time. Each orbit brings Phobos slightly closer, increasing the tidal stress that stretches the moon along the direction pointing toward Mars. Grooves and linear features on Phobos' surface may represent early signs of this tidal stress, fractures created by the stretching forces that will eventually tear the moon apart. The largest crater on Phobos, named Stickney, spans about 9 kilometers across, roughly a third of Phobos' average diameter. The impact that created Stickney came close to shattering Phobos completely, and fractures radiating away from Stickney on the opposite side of Phobos suggest the impact's shockwave traveled through the moon, and created stress fractures where it converged. Had the impactor been slightly larger or faster, Phobos might already exist as a ring of debris rather than a battered moon. From Phobos, Mars would dominate the sky, appearing about 40 times wider than the moon appears from Earth, and covering a huge portion of the visible sky. Phobos orbits faster than Mars rotates, completing an orbit in only 7.5 hours. So from Mars's surface, Phobos rises in the west and sets in the east, moving visibly across the sky in just 4.5 hours. Future observers watching from Mars over years or decades would gradually see Phobos appearing larger as it spirals inward, a visible reminder of its approaching doom. When Phobos finally breaks apart, Mars will gain a ring system that might persist for millions of years before the debris gradually falls into the planet's atmosphere. Saturn's moon, Mimas, carries a crater so large relative to the moon's size that it gives Mimas an uncanny resemblance to the Death Star from Star Wars, though the crater formed millions of years before that fictional space station was imagined. The crater, named Herschel, measures about 130 kilometers across, on a moon only about 400 kilometers in diameter, making the crater 1/3 the moon's diameter. The impact that created Herschel came close to destroying Mimas entirely. And the opposite side of Mimas shows fractures and disrupted terrain, likely caused by shock waves from the impact converging after traveling through the moon's interior. The crater walls rise about 5 kilometers above the floor, and a central peak rises about 6 kilometers above the floor. Features created by the rebound of Mimas's icy crust after the initial compression from the impact. The peak stands higher than any other feature on Mimas, visible from orbit as a prominent spike in the otherwise relatively smooth crater floor. The impact energy must have been tremendous, enough to melt or vaporize a significant fraction of Mimas's volume. Yet somehow, Mimas held together and remained a coherent body. Had the impactor been slightly larger or struck at a slightly higher velocity, Mimas would have shattered into fragments that might have formed a ring or reaccreted into several smaller moons. Despite this violent history, Mimas appears geologically dead, showing no signs of internal activity or surface modification beyond impact cratering. The heavy cratering across the surface indicates the terrain is ancient, dating back billions of years. Mimas's interior likely froze solid early in solar system history, leaving no internal heat source to drive geological activity. The moon's orbit lies too far from Saturn for tidal heating to be significant, unlike closer moons like Enceladus, where tidal forces generate enough heat for geological activity. Mimas thus serves as an example of a small moon that suffered tremendous violence but then settled into geological quiescence, preserving evidence of ancient impacts across its frozen surface. Iapetus, another moon of Saturn, displays one of the most striking visual contrasts in the solar system, with one hemisphere bright white and the other dark brown, creating a two-toned appearance visible even from Earth-based telescopes. The bright terrain, composed of relatively clean water ice, reflects about 50 to 60% of incoming sunlight, similar to fresh snow. The dark terrain, concentrated on the leading hemisphere that faces forward in Iapetus's orbit, reflects only about 3 to 5% of sunlight, darker than asphalt. The boundary between bright and dark terrain is relatively sharp in some areas and gradual in others, creating complex patterns visible in high-resolution images. The dark material probably originated outside Iapetus, perhaps as dust knocked off the distant irregular moon Phoebe by micrometeorite impacts and then spiraling inward towards Saturn. Iapetus, orbiting farther out than the regular moons, would encounter this inward spiraling dust on its leading hemisphere, the side facing forward in its orbit. Over millions of years, a thin coating of dark dust accumulated on the leading hemisphere. This dark coating absorbed more sunlight than the bright ice, warming the surface slightly, causing ice to sublimate from the darkened areas and redeposit on the colder, bright areas, creating a feedback effect that enhanced the contrast over time. Iapetus also hosts an equatorial ridge that runs along or near the equator for about 1,300 kilometers, creating a feature unlike anything seen on other moons. The ridge rises up to 20 kilometers above the surrounding terrain in places, making it one of the tallest features in the solar system relative to the body's size. The ridge consists of a chain of individual peaks and massifs, rather than a continuous wall. And in some regions, the ridge splits into 2 or 3 parallel ridges running alongside each other. The origin remains uncertain, with proposed explanations including ancient tectonic activity, remnants of a collapsed ring system that fell onto the equator, or even material that welled up from below during a period when Iapetus rotated faster and had a more pronounced equatorial bulge. From Iapetus's surface at the base of the ridge, looking up would reveal a mountain wall rising higher than any mountain on Earth, its peak disappearing into the black sky above. Following the ridge would show it extending to the horizon in both directions, curving with the moon's equator, a vast wall encircling the world. The ridge gives Iapetus the appearance of a walnut or a seamed ball, a shape so unusual that early low-resolution images led some to speculate about artificial origins, though higher resolution data confirmed the ridge as a natural geological feature. The combination of the two-toned coloring and the equatorial ridge makes Iapetus one of the most visually distinctive moons in the solar system. Callisto, Jupiter's second largest moon, stands as an example of a world that never underwent full differentiation, remaining a mixed ice rock body throughout its history. Most large moons separated into layers during their formation, with denser rock sinking to form a core and lighter ice rising to form a mantle and crust. Callisto appears to have remained only partially differentiated, with rock and ice mixed throughout much of its interior, possibly with some concentration of rock toward the center, but not a fully separated core. This lack of differentiation makes Callisto unusual among large moons and has implications for its geological history and current structure. The reason for Callisto's incomplete differentiation may relate to the timing and intensity of heating in the early solar system. If Callisto formed slowly, accumulating material gradually, it might never have accumulated enough heat from impacts and radioactive decay to fully melt and allow differentiation. Alternatively, if tidal heating was weak or absent during critical periods, insufficient energy would have been available to melt the interior. The result is a moon with a relatively homogeneous interior, neither fully rocky like terrestrial planets, nor fully layered like differentiated icy moons. This homogeneous structure affects Callisto's response to tidal forces and its ability to generate a magnetic field. Despite its ancient, heavily cratered surface, Callisto shows subtle evidence of an internal liquid layer, probably a subsurface ocean similar to Europa's, but buried deeper and perhaps sandwiched between layers of ice rather than sitting directly on rock. Evidence for this ocean comes from measurements of Callisto's magnetic field by the Galileo spacecraft, which detected variations consistent with a conductive layer inside the Moon. And the most likely conductor at Callisto's temperatures is salty liquid water. The ocean, if it exists, sits beneath perhaps 100 to 200 kilometers of ice and mixed ice rock material, making it far less accessible than Europa's ocean, but potentially equally interesting for understanding conditions that might support life. Pluto's moon Charon, though orbiting a dwarf planet rather than a full planet, deserves mention for its unusual characteristics, particularly the reddish-brown polar cap that covers Charon's north pole. The coloring comes from organic molecules called tholins, but the source of these tholins is not Charon itself, but rather Pluto. Methane gas, escaping from Pluto's thin atmosphere, moves too fast to be recaptured by Pluto's weak gravity, and some of this methane encounters Charon. The methane preferentially condenses at Charon's cold polar regions, where temperatures drop low enough for methane to freeze. Once frozen onto Charon's surface, the methane ice undergoes chemical processing by ultraviolet light from the distant sun and by charged particles from the solar wind. This processing breaks apart methane molecules and reassembles them into more complex organic molecules, the tholins that give the polar region its distinctive reddish-brown color. The process continues gradually, so the tholin deposit grows thicker over time, becoming darker and more deeply colored. The South Pole presumably experienced similar processing during Charon's long winter, though that hemisphere was in shadow during New Horizons' flyby in 2015, preventing detailed imaging of the southern polar region. Charon and Pluto are tidally locked to each other, meaning they always show the same face to each other as they orbit their common center of mass. From Pluto's Charon-facing hemisphere, Charon hangs motionless in the sky, neither rising nor setting but remaining at a fixed position, slowly changing phase as sunlight illuminates different portions, depending on their orbital position. From Charon's Pluto-facing hemisphere, Pluto dominates the sky, appearing about 7 times wider than the Moon appears from Earth, also motionless and unchanging in position. On the far hemispheres of each body, the companion moon never rises, remaining forever below the horizon, creating 2 very different sky experiences, depending on which hemisphere you inhabit. These exceptional moons reveal that moons are far more varied and interesting than simple rocky or icy balls orbiting planets. Each one shaped by unique circumstances and histories that created distinctive characteristics. And while moons orbit their planets, those planets also host orbiting structures of entirely different character, delicate rings of ice and dust, arranged in patterns that reveal hidden gravitational influences. Rings encircling planets appear delicate and ephemeral when viewed from a distance, thin disks of orbiting material that seem impossibly fragile compared to the massive worlds they surround. Yet these structures persist for millions of years and display intricate patterns created by complex gravitational interactions. Every giant planet possesses rings, though they vary enormously in brightness, thickness, and structure. Some rings blaze brilliantly in sunlight, while others hide in darkness, visible only when backlit or observed at specific angles. Saturn's B ring contains mysterious features called spokes, dark radial streaks that appear in images as temporary markings extending across thousands of kilometers of the ring. The spokes appear, persist for a few hours, then fade away, with new spokes forming elsewhere, while old ones disappear. Voyager spacecraft first observed spokes in the early 1980s, and Cassini confirmed they still occur decades later, ruling out explanations based on transient events. The spokes rotate with the ring particles rather than remaining fixed in space, indicating they consist of material actually in orbit rather than shadows or optical effects. The most widely accepted explanation involves electrostatic levitation of fine dust particles above the main ring plane. Saturn's magnetic field and the solar wind create electrical charges on ring particles, and under certain conditions, these charges can become strong enough to lift small dust particles away from the larger ring particles they originally sat on. The lifted dust forms a cloud, hovering slightly above or below the ring plane, appearing dark when seen against the bright ring, and bright when seen against the darkness of space. The spokes appear most commonly when the ring plane passes through Saturn's equator, and the magnetic field geometry creates favorable conditions for electrostatic effects. Watching spokes form in time-lapse images reveals their sudden appearance, as if an invisible brush sweeps across the ring, creating a dark streak where none existed moments before. The spokes then rotate along with the ring particles, stretching and shearing slightly as the inner edge moves faster than the outer edge due to orbital mechanics. After a few hours, the spokes fade as the levitated dust settles back onto the ring plane, or disperses, the electrical conditions that created the levitation changing as Saturn's magnetic field rotates, and the illumination geometry shifts. The phenomenon demonstrates that rings are not static structures, but dynamic environments where electromagnetic forces interact with gravity to create temporary features. Jupiter's gossamer rings, much fainter than Saturn's rings and invisible to early observations, consist of dust kicked off small moons by micrometeorite impacts. Two distinct gossamer rings exist, each associated with a specific small moon. The inner gossamer ring connects to the moon Amalthea, while the outer gossamer ring connects to the moon Thebe. Dust particles ejected from these moons by impacts spread out along their orbital paths, creating a torus of material that encircles Jupiter at the distance of each moon's orbit. The dust particles gradually spiral inward due to drag from Jupiter's magnetic field, and eventually fall into the planet's atmosphere, but new impacts constantly replenish the supply, maintaining the rings as long as the source moons continue to exist. The gossamer rings appear brightest when viewed from behind, backlit by the sun, because fine dust scatters light more efficiently in the forward direction than backward. Viewed from the side illuminated by the sun, the gossamer rings become nearly invisible, contributing to why they remained unknown until the Voyager spacecraft passed through Jupiter's shadow and looked back at the system backlit. The discovery of these faint rings revealed that ring systems can exist even around planets where they are barely visible, maintained by ongoing processes rather than being remnants of a single past event. The main Jovian ring, brighter than the gossamer rings but still faint compared to Saturn's rings, also consists primarily of dust, possibly sourced from the small moons Metis and Adrastea that orbit within the ring. These tiny moons, only a few tens of kilometers across, get sandblasted by high-velocity impacts that eject material into orbit around Jupiter. The ejected material spreads out to form the ring, concentrated near the orbital distance of the source moons, but extending somewhat inward and outward. The ring's vertical thickness, only about 30 kilometers, remains extremely thin compared to its radial extent, creating a flat sheet of orbiting dust, visible as a bright band when viewed edge-on. Uranus possesses narrow, dark rings quite different from Saturn's broad, bright rings, with most of the Uranian rings only a few kilometers wide and separated by wide gaps of nearly empty space. The rings appear almost black, reflecting only about 2% of incoming sunlight, darker than charcoal. The narrow widths and dark composition make the rings difficult to observe. And they were discovered only in 1977, when Uranus passed in front of a star, and astronomers noticed the star briefly dimmed several times before and after the planet itself blocked the starlight. Each dimming corresponded to one of the narrow rings passing between Earth and the star, temporarily blocking a small percentage of the star's light. The ring's narrow widths suggest the presence of shepherd moons, small satellites orbiting just inside and outside each ring, using their gravity to prevent the ring material from spreading out. As ring particles drift outward, the outer shepherd moon's gravity pulls them back inward, while the inner shepherd moon prevents inward drift, confining the ring to a narrow band. Only 2 shepherd moons have been directly observed in the Uranus system, but the narrow structure of several rings suggests more small moons likely exist, too small or too dark to be detected in current images. These shepherding interactions demonstrate how even small moons can have significant effects on ring structure through precisely positioned gravitational influence. The Epsilon ring, Uranus's brightest and widest ring, varies in width from about 20 kilometers at its narrowest to about 96 kilometers at its widest, with the width changing around the ring's circumference. The variation appears to correlate with orbital eccentricity, with the ring wider at points farther from Uranus and narrower at points closer to Uranus. This relationship suggests the ring material responds to changing orbital speeds as it travels around its elliptical path, bunching up where it moves slowly and spreading out where it moves faster. The Epsilon ring also shows internal structure, with higher particle density in the center and lower density at the edges, creating a brightness gradient across the ring's width. Neptune's ring system includes an unusual feature: incomplete rings, called arcs, where material concentrates in specific locations rather than spreading uniformly around the planet. The arcs appear in the outermost ring, named the Adam's ring, which contains most of its material in 5 distinct arcs, while the rest of the ring remains very sparse. The arcs have been named Liberté, Égalité 1, Égalité 2, Fraternité, and Courage, and they persist in their locations rather than spreading out, which orbital mechanics would normally cause to happen over time. The confinement of material into arcs requires some mechanism to counter the natural tendency for ring particles to spread evenly around the orbit. The most likely explanation involves orbital resonances with Galatea, a small moon orbiting just inside the Adam's ring. Galatea's gravity creates periodic perturbations on ring particles, and at specific resonant locations, these perturbations can trap particles and prevent them from spreading. The 42 to 43 resonance appears particularly important meaning particles in the arcs orbit 42 times for every 43 orbits of Galatea, creating a repeating pattern of gravitational tugs that confine particles to specific longitudes. Observations over years have shown the arcs slowly moving and changing slightly in brightness, suggesting the confinement mechanism is not perfect, and some material leaks out of the arcs over time, while other material gets captured. Saturn's rings, despite their prominence and beauty, may be disappearing, with estimates suggesting they might last only another 100 to 300 million years before largely vanishing. The rings lose material through several processes, with ring rain being particularly significant. Fine particles from the rings become electrically charged through interactions with Saturn's magnetic field and ultraviolet light, and these charged particles follow magnetic field lines that lead them into Saturn's upper atmosphere. The infalling particles vaporize and create observable effects in Saturn's atmosphere, allowing the rain rate to be estimated at somewhere between 400 and 2,800 kilograms of material per second. At this rate, the rings are losing mass measurably over time. And since the rings likely contain a fixed amount of material that is not being replenished, the depletion will eventually remove them entirely. The timescale of a few 100 million years seems long by human standards, but represents only a few % of the solar system's age, suggesting Saturn's rings are a temporary feature in geological terms. If we could observe Saturn from 1 billion years ago, it might have had no rings at all, and if we return 1 billion years from now, the magnificent ring system might be gone, leaving only faint traces, or perhaps nothing at all. This realization adds poignancy to our observations of Saturn's rings, suggesting we live in a special time when this particular planet happens to be adorned with a spectacular ring system. The rings might have formed from a moon that wandered too close and was torn apart by tidal forces, or from a collision between moons, or from a comet that passed within Saturn's Roche limit and shattered into fragments. Whatever their origin, the rings represent a temporary decoration, beautiful but impermanent, eventually destined to spiral into Saturn or be lost to other processes. Future astronomers, millions of years from now, might study ancient images and wonder what it was like when Saturn still had its rings. Evidence suggests that Saturn's moon Rhea may have possessed its own ring system in the recent past, though none is currently visible. The Cassini spacecraft detected asymmetries in the charged particle environment around Rhea that could be explained by material orbiting the moon and absorbing particles. The signature resembled what would be expected if several narrow rings circled Rhea, though direct imaging did not reveal any rings. The rings, if they existed, might have been made of very dark material that reflected too little sunlight to be visible. Or they might have been transient, dispersing shortly before Cassini arrived, leaving only indirect evidence in the particle environment. If Rhea did have rings, they would have formed from material ejected by impacts on the moon's surface, similar to how Jupiter's gossamer rings form. The rings would have been unstable over long timescales, with material gradually falling back to Rhea's surface, or being lost to other processes. A ring system around a moon rather than a planet would be unusual, though not impossible, requiring the right combination of impact events and orbital dynamics. The uncertain nature of Rhea's rings illustrates how much we still have to learn about ring systems and the processes that create and destroy them. Even Earth experiences temporary ring-like structures, though they persist for only hours or days rather than millions of years. When large impacts occur on the Moon, they eject material upward. And some of this material can reach high enough altitude and velocity to enter temporary orbit around Earth before falling back to the Moon or Earth. These transient clouds of lunar dust create brief ring-like structures that disperse quickly, but demonstrate that ring formation can happen around any body when the right conditions occur. Permanent Earth rings are unlikely because any long-lived ring material this close to the Sun would be rapidly cleared by solar radiation pressure and interactions with Earth's atmosphere. But brief episodes of ring-like structures remain possible after major lunar impacts. These rings, arcs, spokes, and temporary structures reveal orbital space around planets as far more complex and dynamic than simple empty vacuum, filled instead with particles and dust arranged in patterns determined by gravity, electromagnetism, and the ongoing processes that create and destroy orbiting material. And among all these patterns and structures, certain extremes stand out, records and limits that define the boundaries of what our solar system contains. Every measurable quantity across the solar system spans some range from minimum to maximum, and identifying these extremes reveals the limits of what planetary processes can produce, given the materials and conditions present in our particular star system. Temperature ranges from the coldest permanently shadowed craters to the hottest volcanic vents. Atmospheric pressure from near-perfect vacuum to crushing depths, and physical dimensions from the tallest mountains to the deepest canyons. These extremes often surprise because they exceed what seems possible based on Earth's comparatively moderate conditions. Venus holds the record for the hottest surface temperature in the solar system, at around 900 degrees Fahrenheit or 475 degrees Celsius, maintaining this temperature day and night at the equator and the poles, year-round with minimal variation. The extreme heat results from a runaway greenhouse effect, where the thick carbon dioxide atmosphere traps heat so efficiently that surface temperatures exceed what the direct sunlight alone could provide. The greenhouse warming adds about 400 degrees Celsius to what the temperature would be without an atmosphere, transforming what might be a hot but potentially bearable world into an environment more hostile than the inside of a self-cleaning oven. The heat reaches sufficient intensity to melt lead, which liquefies at around 620 degrees Fahrenheit, well below Venus's surface temperature. Zinc would melt on the hottest days, and many types of glass would soften and deform if left on the surface for extended periods. Electronic components would fail almost instantly, even those designed for high-temperature operation, making Venus an extremely challenging environment for surface missions. The few landers that have reached Venus's surface survived only minutes to a couple of hours before succumbing to the combination of heat and pressure, sending back a handful of images and measurements before contact was lost. Remarkably, Venus reaches these temperatures despite being twice as far from the Sun as Mercury, demonstrating that distance from the Sun matters less than atmospheric composition in determining surface temperature. Mercury, lacking any substantial atmosphere, experiences extreme temperature swings from around 800 degrees Fahrenheit on the day side to minus 300 degrees Fahrenheit on the night side. But its average temperature, and especially its minimum temperature, fall far below Venus's constant furnace heat. The comparison illustrates how atmospheres control planetary climates more powerfully than solar distance alone, a lesson relevant to understanding climate change on Earth and habitability around other stars. At the opposite extreme, the coldest recorded temperatures in the solar system occur not on distant Pluto, but in permanently shadowed craters at the Moon's south pole, where temperatures drop to around 30 Kelvin or minus 243 degrees Celsius. These craters lie in regions where the sun never shines due to the Moon's minimal axial tilt, creating permanent darkness that has persisted for billions of years. Without sunlight to provide warmth, temperatures in these cold traps fall to levels determined only by heat radiating from nearby sunlit regions and the faint infrared glow of space itself, which sits at about 3 Kelvin. The permanently shadowed regions remain cold enough that water ice, if present, would never sublimate, creating stable deposits that could preserve ice for billions of years. Recent observations have confirmed water ice does exist in these craters, likely delivered by comet impacts over geological time, and then cold trapped in the permanent shadows. The ice survives despite the Moon's proximity to the Sun, because the shadowed craters provide protection from sunlight and warmth, demonstrating that local geometry can matter more than average distance when determining whether ice can persist. Pluto's average surface temperature of around minus 380 degrees Fahrenheit actually exceeds the lunar cold trap temperatures, making these shadowed craters the coldest accessible surfaces in the solar system. Mars hosts Olympus Mons, the tallest mountain in the solar system, standing approximately 21.9 kilometers or 13.6 miles high, measured from its base on the surrounding plain to the summit caldera. This height nearly triples Mount Everest's 8.8 kilometers above sea level and exceeds even Everest's approximately 11 kilometers measured from the Tibetan Plateau base. Olympus Mons formed as a shield volcano, with layer upon layer of lava flows building up over millions or billions of years, each eruption adding another thin sheet of basaltic lava that spread across the growing structure's slopes. The volcano could grow to such immense size partly because Mars lacks plate tectonics, meaning the volcanic hotspot remained stationary relative to the surface above it. On Earth, the Pacific plate moves over the Hawaiian hotspot, creating a chain of volcanoes as the plate motion carries each volcano away from the magma source, limiting how large any individual volcano can grow. On Mars, the surface stayed put relative to the magma source beneath Olympus Mons, allowing eruptions to continue building the same structure for perhaps 3 billion years. The lower Martian gravity also allowed the volcano to grow taller before its own weight caused structural failure, supporting heights that would collapse under Earth's stronger gravitational pull. From the summit of Olympus Mons, the horizon lies about 300 kilometers away, due to the curvature of Mars's surface combined with the viewing height, roughly 3 times farther than the horizon appears from Mount Everest's summit on Earth. The base of the volcano lies beyond this horizon, invisible from the top, making it impossible to see the volcano's full extent from any point on its surface. The summit caldera, a complex structure of overlapping collapse pits, measures roughly 80 kilometers across, large enough to contain several major cities. Standing at the caldera's rim and looking across to the opposite side would present a view of cliffs and terraces extending to a barely visible far rim at the edge of sight. Mars also claims the record for the deepest and longest canyon system, Valles Marineris, which stretches roughly 4,000 kilometers along the Martian equator, about the width of the United States from coast to coast. The canyon reaches depths of up to 7 kilometers below the surrounding plateau, in some sections, creating vertical relief that dwarfs the Grand Canyon's 1.8 kilometers maximum depth. The Grand Canyon could fit entirely within some of Valles Marineris' wider sections, with room to spare, and the length of the Martian canyon system exceeds the Grand Canyon's length by more than tenfold. Valles Marineris likely formed through a combination of tectonic fracturing and erosion, with the initial rifting occurring when the nearby Tharsis volcanic region rose and created extensional stresses in the surrounding crust. These stresses opened deep fractures that then widened over time through various erosion processes, including possible water flow, landslides, and sublimation of subsurface ice. The canyon walls show extensive layering visible in high-resolution images, with each layer representing a different episode of deposition or volcanic activity in Mars's ancient past. Some sections display evidence of water seepage from the canyon walls, suggesting subsurface aquifers may still exist at depth, occasionally releasing water that evaporates in the thin Martian atmosphere. Jupiter possesses the strongest magnetic field of any planet, with a field strength at the cloud tops reaching approximately 20,000 times Earth's magnetic field strength. The field originates deep within Jupiter's interior, where immense pressure compresses hydrogen into a liquid metallic state that conducts electricity. Convection currents in this metallic hydrogen layer create electric currents, and these currents generate the magnetic field through the same dynamo process that operates in Earth's liquid iron core. Jupiter's enormous size and rapid rotation create ideal conditions for a powerful dynamo, resulting in a magnetic field that extends millions of kilometers into space. The magnetosphere, the region of space dominated by Jupiter's magnetic field, extends outward roughly 5 million kilometers on the sunward side and stretches into a long tail extending beyond Saturn's orbit on the night side, though the exact dimensions vary depending on solar wind pressure. If the magnetosphere were visible to human eyes, it would appear from Earth as several times larger than the full moon, despite Jupiter's great distance. The magnetosphere traps charged particles from the solar wind and from volcanic eruptions on Io, creating intense radiation belts, far more dangerous than Earth's Van Allen belts. Radiation levels near Io's orbit, deep within Jupiter's magnetosphere, reach approximately 1 million rads per day, a dose that would be fatal to humans within minutes and damaging to electronics within hours. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, required extensive radiation shielding and careful trajectory planning to survive long enough to complete its mission. And even with precautions, radiation gradually degraded some instruments and systems. Future missions to Jupiter's moons must account for this intense radiation environment, either through heavy shielding, short visit durations, or carefully planned orbits that minimize time in the most intense radiation zones. Neptune holds the record for the fastest sustained winds measured in the solar system, with wind speeds reaching approximately 1,200 miles per hour or 2,100 kilometers per hour near the equator. These supersonic winds faster than the speed of sound in Earth's atmosphere, glow despite Neptune receiving about 900 times less solar energy per unit area than Earth, making the energy source somewhat mysterious. The winds appear to be powered primarily by internal heat, rather than solar heating, as Neptune radiates about 2.6 times more energy into space than it receives from the Sun. The mechanism by which Neptune's interior generates this excess heat remains uncertain, though possibilities include ongoing gravitational contraction, separation of helium and other compounds in the interior releasing gravitational energy, or residual heat from the planet's formation 4.6 billion years ago. Whatever the source, the internal heat drives powerful convection in Neptune's atmosphere, and the planet's rapid 16-hour rotation organizes this convection into strong jet streams that circle the planet. The combination of internal heating, rapid rotation, and low solar input creates atmospheric dynamics quite different from Earth's, resulting in the extreme wind speeds observed. From Neptune's perspective, these winds represent normal weather, the baseline atmospheric circulation pattern, rather than an unusual storm. Clouds of methane ice crystals race around the planet at these tremendous speeds, forming and dissipating within hours or days as atmospheric dynamics shift. The white clouds appear bright against Neptune's deep blue atmosphere, creating photogenic contrasts that have been captured by Voyager 2 and more recently by Hubble and the James Webb Space Telescopes. The storms themselves come and go over years, with the Great Dark Spot observed by Voyager disappearing by the time Hubble observed Neptune a few years later, only to be replaced by new dark spots in other locations. Pluto and Charon form what might be better called a binary dwarf planet system rather than a planet-moon pair, because Charon's mass reaches about 12% of Pluto's mass, and its diameter measures about half of Pluto's diameter. This makes Charon the largest moon relative to its primary in the solar system, with the mass ratio and size ratio both exceeding any other planet-moon pair. The center of mass around which both bodies orbit, called the barycenter, lies about 600 kilometers above Pluto's surface, well outside Pluto's physical radius, meaning Pluto and Charon both orbit a point in empty space between them, rather than Charon orbiting around a point inside Pluto. This configuration creates unique dynamics where both bodies are tidally locked to each other, always showing the same face to their companion, and both orbit the barycenter with the same period of 6.4 days. From Pluto's Charon-facing hemisphere, Charon hangs motionless in the sky, at a fixed position, never rising or setting, slowly cycling through phases, from full Charon to new Charon, as their orbital positions change relative to the Sun. From Charon's Pluto-facing hemisphere, Pluto similarly remains stationary in the sky, appearing about 7 times larger than the Moon appears from Earth. Observers on the opposite hemispheres of each body never see their companion at all, living in a universe where their neighboring world remains permanently below the horizon. The mutual tidal locking occurred relatively early in the system's history, with tidal forces dissipating energy until the rotations synchronized with the orbital period, a state of minimum energy that represents the final endpoint of tidal evolution. Most large moons are tidally locked to their planets, always showing the same face to the primary. But the planet typically is not locked to the Moon due to the planet's much larger mass. The Pluto-Charon system's more balanced mass ratio allowed mutual locking to occur within the age of the solar system, creating the current configuration where both bodies participate equally in the tidal lock. Io experiences more volcanic activity than all other known solid bodies in the solar system combined, with hundreds of active volcanoes and eruption rates that completely resurface the moon every million years or so. This extreme activity results from intense tidal heating generated by Io's orbital resonance with Europa and Ganymede, combined with Jupiter's immense gravity. The tidal forces flex Io's interior continuously, generating friction that melts rock and drives it to the surface through volcanic vents. The total heat flow from Io's interior reaches about 2 watts per square meter, averaged across the entire surface, roughly 40 times Earth's average heat flow, and sufficient to keep much of Io's interior molten. The constant resurfacing erases impact craters as fast as they form, making Io's surface the youngest in the solar system, with virtually no craters detectable in even the highest resolution images. The fresh volcanic deposits paint Io in yellows, oranges, reds, and blacks from various sulfur compounds and silicate lavas, creating the most colorful solid surface in the solar system. Volcanic plumes rise hundreds of kilometers above the surface, creating umbrella-shaped deposits of ejected material that fall back to create dark or bright rings around active vents. The combination of extreme activity, varied surface compositions, and ongoing resurfacing makes Io a world in constant visible change, looking measurably different from one decade to the next. Europa claims the record for the smoothest solid surface in the solar system, with minimal topographic variation compared to other similar-sized bodies. The surface consists of water ice that has been recently renewed through geological processes, with few impact craters surviving long enough to contribute to roughness. The smoothness results from ice tectonics, where the ice shell floats on the subsurface ocean and can move and deform, closing and erasing old features while creating new ones. Tidal flexing also contributes by cracking the ice and allowing warm ice or even liquid water from below to well up and fill low areas, gradually smoothing the surface over time. The few topographic features that exist on Europa, mainly ridges and small ice rafts, rarely exceed a few hundred meters in height, and the surface shows no mountains or deep valleys comparable to those on rocky bodies or even on other icy moons. This smoothness means that if Europa were shrunk to the size of a billiard ball, it would be smoother than an actual billiard ball, meeting or exceeding the manufacturing tolerances for professional billiard equipment. The smooth surface contrasts sharply with the heavily cratered roughness of Callisto or the fractured chaos of Enceladus, demonstrating how ongoing geological activity can erase topography and maintain a nearly level surface even over billions of years. These extremes, from the hottest to the coldest, the tallest to the smoothest, the windiest to the most volcanic, define the range of conditions and features our solar system can produce. And these extreme conditions create visual appearances determined by how light interacts with different materials and atmospheres, painting the planets and moons in colors that tell stories about composition and chemistry. Color across the solar system arises from the interaction between sunlight and surface materials, or atmospheric gases, with different substances absorbing certain wavelengths while reflecting others to create the hues we observe. The variety of compositions, from iron oxides to sulfur compounds to complex organic molecules, creates a palette ranging from pale blues through vibrant oranges to deep blacks. Understanding why each world appears the color it does requires examining both the chemical composition of visible surfaces and the physical processes that create and modify these materials. Uranus and Neptune both appear blue due to methane in their atmospheres absorbing red wavelengths of sunlight and allowing blue wavelengths to be reflected back to space. Yet Neptune appears noticeably deeper and richer blue than Uranus's pale cyan color. Both planets have similar atmospheric compositions, dominated by hydrogen and helium, with a few % methane, so the methane absorption alone cannot explain the color difference. Uranus's atmosphere contains a layer of haze at altitude that scatters some blue light before it penetrates deep into the atmosphere, giving Uranus a paler, more whitish blue appearance by mixing white scattered light with the blue from methane absorption. Neptune lacks this high-altitude haze layer, or has less of it, allowing incoming sunlight to penetrate deeper into the atmosphere before being reflected. The deeper penetration allows methane to absorb red light more completely, creating a purer, darker blue appearance. Additionally, Neptune's atmosphere appears to contain an unknown component that enhances red absorption beyond what methane alone can explain, making the blue even more saturated. The identity of this component remains uncertain despite decades of study, though possibilities include complex hydrocarbons or other trace gases that absorb in the red portion of the spectrum. The difference between the two ice giants demonstrates that subtle atmospheric variations can create noticeably different appearances, even when overall compositions are similar. Io displays the most colorful solid surface in the solar system, with yellows, oranges, reds, whites, and blacks creating a mottled appearance that resembles a pizza or a Jackson Pollock painting, depending on which description appeals to you. The colors come from sulfur compounds in various chemical forms and oxidation states, each form producing a different color depending on its molecular structure and temperature history. Bright yellow areas represent freshly deposited sulfur, likely erupted in molten form and then quickly frozen, while darker yellows and oranges indicate sulfur that has been exposed to sunlight and space radiation for longer periods and has undergone chemical changes. Red and brown materials probably represent longer sulfur chains and more complex sulfur compounds created through radiation processing and heating cycles, while black areas may be silicate lava flows or heavily processed sulfur compounds that have darkened over time. White and bright patches represent sulfur dioxide frost, either erupted from volcanic vents or condensed from volcanic plumes that reach high altitude and freeze. The complex patterns result from ongoing volcanic activity, constantly depositing new materials, while radiation and thermal cycling modify existing deposits, creating a surface that records both current eruption patterns and the cumulative effects of space weathering. The colors visible to human eyes would appear slightly different from the enhanced color images often published, which emphasize subtle color variations to show geological details more clearly. Actual human vision on Io's surface would see the yellows and whites clearly, with the reds and browns more subdued, and the black areas appearing dark gray or brown rather than truly black. The sunlight at Io's distance appears somewhat dimmer than on Earth, though still bright enough for comfortable vision. And the lack of atmospheric scattering means shadows would be sharp and black, while illuminated surfaces would appear in harsh, direct light without the soft, diffuse lighting Earth's atmosphere provides. Mars's two small moons, Phobos and Deimos, appear among the darkest objects in the solar system, reflecting only about 6% of the sunlight that hits them, darker than fresh asphalt, which reflects around 10 to 15%. The dark color suggests a composition rich in carbonaceous material, possibly similar to the carbon-rich meteorites called carbonaceous chondrites that represent some of the most primitive materials in the solar system. The darkness indicates these moons likely formed in the outer solar system, where carbon-rich materials were more common, then somehow ended up orbiting Mars, either through capture or through a more complex formation scenario. The dark surfaces show subtle color variations in detailed spectroscopic observations, with reddish tinges in some regions, possibly indicating space weathering or surface dust, and slightly bluer areas, perhaps exposing fresher, less weathered material. Impact craters on both moons excavate material from below the surface layer, sometimes revealing slightly brighter material beneath the dark surface coating, suggesting the surface darkness may be enhanced by space weathering that accumulates radiation damage and micrometeorite impacts over billions of years. Despite their darkness, both moons are visible in telescopes from Earth when positioned favorably relative to Mars's bright disk, though they appear as faint points requiring patience and dark skies to observe clearly. Saturn appears golden or butterscotch-colored compared to Jupiter's more prominent brown and white bands, a difference that comes from subtle variations in atmospheric composition and cloud structure, despite both planets having similar overall makeup. Saturn's upper atmosphere contains more haze and fewer of the colored compounds that create Jupiter's brown belts, possibly because Saturn's weaker gravity and lower atmospheric pressure allow hazes to form higher in the atmosphere, where they scatter light differently. The ammonia ice crystals that dominate Saturn's upper clouds appear white or pale yellow depending on trace contaminants. And the relative lack of darker compounds compared to Jupiter creates the softer, more muted color palette. The golden hue becomes more pronounced when viewing Saturn's northern hemisphere during northern summer, when increased sunlight drives photochemical reactions that create more complex hydrocarbons and hazes. The seasonal changes occurring over Saturn's 29-year orbit create subtle variations in color and cloud structure that have been documented through decades of Earth-based and spacecraft observations. The rings, composed of relatively clean water ice, appear brilliant white or slightly off-white in true color images, contrasting with the planet's golden globe and creating Saturn's distinctive appearance that makes it arguably the most aesthetically beautiful planet in the solar system. Enceladus reflects nearly 100% of incoming sunlight, making it the brightest object in the solar system relative to its size and the most reflective surface known. The extraordinarily high reflectivity results from the surface being continuously coated with fresh ice from the South Polar geysers, which erupt water vapor and ice crystals that fall back onto the surface across the entire moon due to Enceladus's weak gravity. The constant deposition of fresh ice covers older, darker material before space weathering can significantly darken the surface. maintaining the bright white appearance across billions of years. The reflectivity means that, despite Enceladus being much farther from the Sun than Earth and receiving correspondingly less sunlight, the surface appears brilliant white to human eyes, glaring and difficult to look at directly, just as fresh snow appears on Earth. Photographs of Enceladus often show it glowing against the darkness of space, or appearing as a bright crescent when backlit by the sun, the fresh ice scattering light efficiently in all directions. The brightness contrasts dramatically with nearby moons like Mimas or Tethys, which are also icy but significantly darker due to space weathering, accumulating on surfaces that are not regularly renewed with fresh material. Earth appears as a blue marble from space, a description popularized by the Apollo 17 photograph, taken in 1972, showing the fully illuminated Earth from space. The blue color comes from two sources: the blue of the oceans, which cover about 70% of Earth's surface and absorb red wavelengths while reflecting blue, and the blue of the atmosphere itself, which scatters blue light more efficiently than red light through a process called Rayleigh scattering. The same scattering process makes Earth's sky appear blue from the surface, with the scattered blue light creating a soft glow around the planet visible from space. The white swirls are clouds and ice caps, with water vapor condensing into droplets that scatter all wavelengths equally, and thus appear white. The brown and green areas are continents, with colors depending on vegetation coverage, soil type, and rock composition. Deserts appear tan or brown, forests appear dark green, grasslands lighter green, and exposed rock can appear grey, red, or brown depending on mineral composition. The color variations create complex patterns that change with seasons. As vegetation grows and dies back, snow and ice caps expand and contract, and atmospheric circulation patterns shift cloud distributions. From distant spacecraft beyond the orbit of Neptune, looking back at the inner solar system, Earth appears as a pale blue dot, showing almost no detail, just a tiny point of blue light that could easily be mistaken for a reflection or image artifact. The famous pale blue dot image, taken by Voyager 1 from 6 billion kilometers away, shows Earth occupying less than a single pixel, the oceans and atmosphere combining to create a faint blue tint, but no other features visible. The image dramatically illustrates Earth's small size and isolation in the vastness of space, making visual the concept that all of human history and experience has occurred on this tiny speck, barely visible from the outer reaches of the solar system. Ganymede displays a two-toned appearance, with about 40% of the surface covered in dark ancient terrain, and the remaining 60% covered in bright young terrain, creating a patchwork pattern visible in images. The dark terrain represents the original ancient icy crust, billions of years old, heavily cratered and darkened by billions of years of space weathering, including radiation damage, micrometeorite impacts, and implantation of dark particles. The bright terrain formed more recently, perhaps 1 to 2 billion years ago, when tectonic processes fractured and separated regions of the old crust and filled the gaps between them with fresh ice from below. The boundary between dark and bright terrain appears sharp in many places, with relatively young bright terrain abutting ancient dark terrain across a distinct line. The bright terrain shows parallel grooves and ridges, indicating it formed through tectonic extension and possibly cryovolcanism, processes that brought fresh ice to the surface and created the younger, brighter appearance. Over time, space weathering will gradually darken the currently bright terrain, but for now, the contrast between old and new remains visible, creating Ganymede's distinctive appearance that tells a story of geological renewal happening selectively across parts of the surface while other areas remain ancient and unchanged. The colors described here represent true color as the human eye would perceive it. Though many published images of solar system bodies use enhanced color or false color to highlight compositional differences invisible to human vision. Infrared images might show temperature differences or mineral compositions as colors. Ultraviolet images might reveal hazes or auroral glows, and composite images combining different wavelengths create views that convey scientific information but do not represent the actual visual appearance. The distinction matters when trying to envision what these worlds would really look like to human eyes. Though the false color images often reveal important details that true color images would miss. These colors create the visual diversity of the solar system, painting each world in hues determined by chemical composition and physical processes. While beneath and around these colored surfaces, invisible forces shape environments through magnetic fields and radiation that instruments detect but eyes cannot see. Magnetic fields surround some planets and moons, creating invisible structures that deflect charged particles from the solar wind and trap radiation in belts of high-energy particles orbiting in the magnetic field geometry. These fields arise from dynamo processes in electrically conductive fluid layers inside the body, usually liquid metal in rocky planets or liquid metallic hydrogen in gas giants. The field strength, orientation, and structure varies dramatically across different bodies, with some showing organized dipole fields, similar to a bar magnet, while others display complex tilted or offset fields that create asymmetric magnetospheres. Mercury possesses a magnetic field despite its small size, though the field strength measures only about 1% of Earth's field strength. Weak, but definitely present. The field's existence was surprising when discovered by Mariner 10, because Mercury rotates slowly with a day lasting 58 Earth days. And conventional dynamo theory suggested such slow rotation might not generate sufficient field strength. The field's center is offset northward from Mercury's center by about 20% of the planet's radius, creating a lopsided magnetosphere stronger in the northern hemisphere than the southern hemisphere. This offset creates unusual consequences for how the solar wind interacts with Mercury's surface. The southern hemisphere's weaker magnetic protection allows solar wind particles to reach closer to the surface, potentially interacting with surface materials and creating localized space weathering patterns that differ between hemispheres. The magnetosphere itself extends only a few planetary radii into space, much smaller than Earth's magnetosphere, and the solar wind compresses it significantly on the day side while stretching it into a long tail on the night side. The small size means Mercury's magnetosphere responds rapidly to changes in solar wind pressure, fluctuating significantly as the sun's output varies. The heat from the nearby sun and Mercury's slow rotation create extreme temperature differences between day and night sides, and these temperature variations may affect how the core convects and generates the magnetic field. The exact mechanism remains uncertain, with some models suggesting the outer liquid iron core convects, while an inner solid core grows slowly over time, extracting heat and driving the dynamo. Other models invoke more exotic processes, like magnetic field generation, in a solid, partially molten layer through thermoelectric effects. Resolving these questions requires better understanding of Mercury's interior structure, information that future missions may provide through more detailed gravity and magnetic field measurements. Ganymede stands as the only moon in the solar system known to generate its own magnetic field from an internal dynamo, creating a miniature magnetosphere embedded within Jupiter's much larger magnetosphere. The field strength at Ganymede's surface reaches about 700 nanoteslas, roughly 1% of Earth's field strength, but strong enough to create a well-defined magnetosphere that carves out a cavity in Jupiter's magnetic field. The magnetosphere protects some portions of Ganymede's surface from Jupiter's intense radiation environment, creating auroral ovals at high latitudes, where charged particles funnel down magnetic field lines and interact with the tenuous atmosphere. The magnetic field implies Ganymede has a liquid iron core actively convecting and generating the field through dynamo action, requiring sufficient heat to keep the core liquid despite the moon's great distance from the sun and relatively small size. Tidal heating from orbital resonances with Europa and Io may provide enough energy, or radioactive decay in Ganymede's rocky interior might supply the necessary heat. The field has been measured in detail by multiple spacecraft flybys, revealing it has a tilted dipole structure with the magnetic axis offset from the rotation axis by about 10 degrees, similar to Earth's magnetic field geometry, though much weaker. The interaction between Ganymede's magnetosphere and Jupiter's magnetosphere creates complex plasma physics as the two magnetic fields press against each other and reconnect, transferring energy and particles between the systems. Ganymede orbits within one of Jupiter's radiation belts. So charged particles, trapped in Jupiter's field, constantly bombard Ganymede's magnetosphere from outside, creating dynamic conditions quite unlike the relatively stable environment Earth's magnetosphere experiences, interacting primarily with the solar wind. Understanding this embedded magnetosphere provides insights into how magnetic fields can protect moons and possibly exoplanets orbiting close to strongly magnetic parent bodies. Venus lacks an intrinsic magnetic field from an internal dynamo, probably because its slow 58-day rotation rate and possibly different core composition or state prevent the generation of a self-sustaining field. However, Venus does create a weak induced magnetosphere through the interaction between the solar wind and the planet's upper atmosphere. As solar wind plasma flows past Venus, it encounters the ionized upper atmosphere and drapes around it, creating a bow shock and magnetotail, similar in shape to planetary magnetospheres, but powered by external solar wind rather than an internal magnetic field. The induced magnetosphere provides minimal protection against solar wind erosion of the atmosphere, allowing charged particles to strike the upper atmosphere directly and gradually strip away lighter elements over geological time. This atmospheric loss has likely been significant over Venus's history, possibly contributing to the planet's current extreme atmospheric composition by preferentially removing lighter gases like hydrogen, while heavier gases like carbon dioxide, remained. The lack of magnetic protection may also have allowed Venus's water to be lost, with solar ultraviolet breaking apart water molecules into hydrogen and oxygen, and the unprotected hydrogen escaping to space, while oxygen combined with surface rocks. The bow shock forms about 2,000 kilometers above Venus's surface on the sunward side, much closer than Earth's bow shock, which forms about 10 Earth radii away, the difference reflecting the absence of a strong planetary magnetic field pushing back against the solar wind. The magnetotail extends downwind for millions of kilometers, shaped by the solar wind dragging ionized atmospheric particles away from the planet. Observations of the induced magnetosphere show significant variability depending on solar wind conditions, with the structure compressing during periods of high solar wind pressure and expanding during quiet periods, the magnetosphere responding almost immediately to changing external conditions. Mars presents a complex magnetic situation, lacking a global magnetic field today, but possessing strong localized magnetic fields frozen into ancient rocks in the southern highlands. These crustal magnetic fields reach intensities of up to 1,500 nanoteslas in some locations, stronger than Earth's field at the surface in those specific areas, though the fields are patchy and irregular rather than forming an organized global structure. The crustal magnetism represents a fossil record of Mars's early magnetic field, created when Mars had an active dynamo billions of years ago, and then frozen into rocks as they cooled below the Curie temperature, where magnetic minerals lock in their magnetization. The pattern of magnetized and non-magnetized regions tells a story of Mars's geological history. The southern highlands show strong magnetization, suggesting they formed while the global dynamo was still active, more than 4 billion years ago. The northern lowlands show almost no crustal magnetism, suggesting either they formed after the dynamo shut down or subsequent geological activity reheated and demagnetized them. Large impact basins show distinctive magnetic patterns, with strong fields in concentric rings around the basin edges and weak fields in the basin centers. Patterns created when the impact heated crustal rocks above the Curie temperature and demagnetized them, while rocks farther from the impact remained magnetized. The shutdown of Mars's global magnetic field, whenever it occurred, had profound consequences for the planet's atmospheric evolution. Without magnetic protection, the solar wind could directly strip away atmospheric gases, accelerating the loss of Mars's early, thicker atmosphere and contributing to the planet's transformation from a warmer, wetter world to the cold, dry desert it is today. Measurements by the MAVEN spacecraft orbiting Mars have directly observed atmospheric loss processes continuing today, with ions being picked up by the solar wind and swept away at rates that would remove substantial atmosphere over billions of years. The crustal magnetic fields provide some localized protection, creating mini magnetospheres that shield small regions of the surface, but cannot replace the global protection a planetary-scale magnetic field would provide. Jupiter's radiation belts contain the most intense radiation environment in the solar system, other than the Sun itself, with energetic particle fluxes that would deliver fatal radiation doses to unprotected humans in minutes and damage spacecraft electronics within hours. The radiation consists primarily of electrons and protons trapped in Jupiter's magnetic field, spiraling back and forth along magnetic field lines between the north and south magnetic poles. The particles gain energy from several sources, including the solar wind and from the acceleration that occurs when Jupiter's rapidly rotating magnetic field drags particles around with it, creating a vast spinning system of energetic charged particles. The most intense radiation surrounds the orbit of Io, where volcanic eruptions inject ions of sulfur and oxygen into the magnetosphere, and these ions become ionized and accelerated to high energies by electromagnetic forces. The Io plasma torus, a donut-shaped region of charged particles surrounding Jupiter at Io's orbital distance, glows faintly in ultraviolet light from the excited ions. Material from this torus feeds the radiation belts both inward and outward from Io's orbit, creating dangerous conditions for spacecraft trying to visit Jupiter's moons. The Europa Clipper mission, planned to orbit Jupiter and make multiple close flybys of Europa, uses a carefully designed orbit that spends as little time as possible in the most intense radiation zones, dipping in quickly for each flyby and then retreating to safer distances. The radiation hazard affects not just electronics, but also scientific instruments and structural materials, with cumulative radiation damage degrading performance over time. The Galileo spacecraft, which orbited Jupiter for 8 years, experienced gradual degradation of its camera and other instruments despite radiation-hardened design, and mission planners had to carefully ration use of instruments to preserve them for the most scientifically valuable observations. Future missions to the Jupiter system face similar challenges, requiring either short mission durations, heavy shielding, or orbits that minimize radiation exposure, all of which constrain mission design and capabilities compared to exploration of less hazardous destinations. Uranus and Neptune both possess magnetic fields tilted dramatically relative to their rotation axes and offset significantly from their centers, creating highly asymmetric magnetospheres unlike any other planets. Uranus's magnetic field tilts about 60 degrees from the rotation axis, and the field's center is offset from the planet's center by about 1/3 of the planet's radius. Neptune's field shows similar characteristics with a 60-degree tilt and significant offset. These unusual field geometries create magnetospheres that wobble and tumble as the planets rotate, with magnetic field lines sweeping through complex patterns as the tilted fields spin. The origin of these unusual field configurations remains somewhat mysterious, though the most widely accepted explanation involves the magnetic field being generated not in a spherical core, but in a thick conducting shell in the outer portion of the interior, where pressure is sufficient to make water, ammonia, methane ices electrically conductive. Dynamo action in this shell, rather than in a central core, would naturally produce an offset, tilted field, matching observations. The exact depth and thickness of this conducting layer depends on the temperature and pressure profile inside each planet, quantities that remain poorly constrained by current observations. The wobbling magnetospheres create unusual conditions for any charged particles trapped in them, with particles experiencing wildly varying magnetic field orientations as the planets rotate. This likely prevents stable trapped radiation belts from forming as they do around Earth and Jupiter, though some energetic particles probably do get temporarily trapped before being lost. The interaction between these wobbling magnetospheres and the solar wind creates time-varying bow shocks and magnetotails that sweep through space as the planets rotate, conditions quite unlike the relatively stable magnetospheric structures around planets with aligned magnetic fields. Saturn's magnetic field aligns almost perfectly with the rotation axis, within less than 1 degree, making it unique among the giant planets, and creating a mystery about how to determine the planet's internal rotation period. On planets with tilted magnetic fields, the wobble of the magnetic field as the planet rotates creates a clear periodic signature that reveals the rotation period. Saturn's nearly perfect alignment means the magnetic field provides no such signature, and other methods like tracking cloud features are complicated by differential rotation in the atmosphere. Determining Saturn's true internal rotation period required careful analysis of radio emissions and subtle periodicities in the magnetosphere, finally yielding an estimate of about 10 hours, 33 minutes, though uncertainty remains. The well-aligned field creates a highly symmetric magnetosphere, a textbook example of how magnetic fields should theoretically look around a rotating planet. The field extends about 20 to 25 times Saturn's radius on the sunward side before being compressed by solar wind pressure, and stretches into a long tail on the night side, extending millions of kilometers downstream. The magnetosphere is populated by particles from several sources, including the solar wind, Titan's atmosphere, and Enceladus's geysers, creating a complex plasma environment with multiple ion populations interacting electromagnetically. The interaction between Enceladus's water vapor plumes and Saturn's magnetic field creates interesting plasma physics and may generate radio emissions detectable from Earth. The heliopause, the boundary where the solar wind from our Sun can no longer push back against the interstellar medium, lies at about 120 astronomical units from the Sun, based on measurements from the Voyager spacecraft. Both Voyager 1 and Voyager 2 have crossed this boundary into interstellar space, the first human-made objects to leave the Sun's domain and enter the space between stars. The crossing occurs where the outward pressure from solar wind particles balances the inward pressure from the interstellar medium, creating a boundary region where the magnetic field orientation changes and particle populations shift from solar-dominated to interstellar-dominated. The heliopause distance varies depending on direction and solar activity levels, expanding when the solar wind is strong and contracting during solar minimum when the solar wind weakens. The boundary is not perfectly smooth, but shows structure and possibly temporal variations as the solar wind buffets against the interstellar medium. Beyond the heliopause, the Voyager spacecraft continued to send back data about conditions in interstellar space, measuring magnetic fields, cosmic rays, and plasma properties in a region no spacecraft had reached before. This exploration continues as long as the spacecraft power supplies and instruments remain functional, providing humanity's first direct measurements of the local interstellar medium. These invisible magnetic fields and radiation environments shape the space around planets and moons just as profoundly as gravity shapes orbits, creating protective bubbles, dangerous radiation zones, and dynamic boundaries where different plasma populations meet and interact. And within these magnetic environments and on the surfaces below, time itself takes on different meanings as days and years vary wildly across different worlds. Time on Earth flows in familiar rhythms of 24-hour days and 365-day years, But these particular durations result from Earth's specific rotation rate and orbital period. And other worlds divide time quite differently, depending on how fast they spin and how long their orbits take. The relationship between a world's day, its year, and sometimes resonances between the two creates temporal experiences ranging from the nearly familiar to the utterly alien. Understanding how time works on other worlds requires distinguishing between sidereal periods measured against the stars and solar periods measured from sunrise to sunrise, a distinction that becomes important when days and years have unusual relationships. Venus rotates backward compared to most planets, spinning in the opposite direction relative to its orbital motion. And this retrograde rotation means the Sun rises in the west and sets in the east from Venus's surface. The rotation is also extremely slow, with Venus taking about 243 Earth days to complete one rotation relative to the stars. The orbital period, the time to complete one trip around the Sun, takes about 225 Earth days. The combination of slow retrograde rotation and the shorter orbital period creates unusual consequences for how long a day lasts, measured from sunrise to sunrise. Because Venus rotates backward while it orbits forward, the rotation and orbital motion partially cancel each other out when determining how long the Sun takes to return to the same position in the sky. The solar day on Venus, measured from noon to noon, lasts about 117 Earth days, meaning from one sunrise to the next sunrise takes 117 days. This makes the Venusian solar day longer than the Venusian year, creating the unusual situation where the Sun completes a full circuit of the sky less than twice per Venusian year. A calendar for Venus would need to account for years containing only about 1.9 days, a temporal relationship unlike anything in human experience. Standing on Venus's surface and watching the Sun move across the sky would reveal extraordinarily slow motion, the Sun taking 58 Earth days to travel from eastern horizon to western horizon. Then another 58 Earth days of night before sunrise occurs again in the west. The slow solar motion means shadows would move almost imperceptibly over hours, and day and night would each last nearly 2 Earth months. The thick atmosphere scatters light so effectively that twilight would extend for many days at the beginning and end of each daylight period, creating long transition phases between full day and full night. The entire temporal experience would feel alien, with the familiar rhythm of daily cycles stretched to month-long durations. Mercury demonstrates a different kind of unusual day-year relationship through its 3-2 spin-orbit resonance, where Mercury rotates exactly 3 times for every 2 orbits around the Sun. This resonance creates a situation where Mercury's sidereal day, measured relative to the distant stars, lasts 58.6 Earth days, and its orbital period lasts 88 Earth days, making the year exactly 1.5 times as long as the sidereal day. The resonance locks these 2 periods into a stable relationship maintained by tidal forces from the Sun, which have gradually slowed Mercury's rotation over billions of years until it reached this resonant configuration. The 3-2 resonance creates an unexpected consequence for how long the solar day lasts, measured from sunrise to sunrise. Because of the relationship between rotation and orbital motion, one solar day on Mercury lasts exactly 2 Mercurian years, or about 176 Earth days. This means the sun rises, crosses the sky, sets, then after a long night, rises again only after Mercury has completed 2 full trips around the sun. The solar motion across the sky shows unusual behavior, with the sun sometimes appearing to stop, reverse direction, and then continue forward again, due to Mercury's changing orbital speed as it moves through its elliptical orbit. From certain longitudes on Mercury's surface, the sun would perform a complete double sunrise, rising partway above the horizon, then sinking back below it, then rising again and continuing across the sky. This bizarre phenomenon occurs because Mercury's orbital speed varies significantly as it moves through its eccentric orbit, sometimes moving faster than the rotational speed that would carry a surface feature into sunlight, and sometimes moving slower. When orbital motion temporarily overtakes rotational motion near perihelion, the sun appears to reverse direction in the sky, creating the double sunrise. No other planet displays this particular behavior, making Mercury's solar day uniquely strange among the planets. Jupiter rotates faster than any other planet in the solar system, despite being the largest, completing one rotation in about 9 hours 50 minutes at the equator. The rapid rotation creates significant equatorial bulge, with the equatorial diameter being about 7% larger than the polar diameter due to centrifugal forces flattening the planet. The rotation is differential, meaning different latitudes rotate at different speeds, with equatorial regions completing a rotation faster than polar regions. This differential rotation drives powerful atmospheric dynamics and helps create the prominent banded appearance of alternating dark belts and bright zones that circle the planet parallel to the equator. The short day, combined with Jupiter's large size, creates surface speeds at the equator of about 28,000 miles per hour, roughly 12 kilometers per second. This tremendous speed contributes to the strength of Jupiter's magnetic field through the dynamo effect and influences how atmospheric features develop and evolve. The rapid rotation organizes atmospheric flow into stable jet streams that persist for decades or longer, creating the bands visible from Earth-based telescopes. The Great Red Spot and other long-lived storms rotate within these jet streams, drawing energy from the turbulent atmosphere around them, while maintaining their structures across centuries. Measuring Jupiter's rotation period precisely requires careful observation, because different atmospheric features at different latitudes rotate at different rates. Astronomers define different rotation periods for different systems, with System 1 applying to equatorial regions rotating in about 9 hours, 50 minutes, and System 2 applying to higher latitudes, rotating in about 9 hours, 55 minutes. Radio emissions from Jupiter's magnetic field provide the most accurate measurement of the deep interior rotation, yielding a period of 9 hours, 55 minutes, and 30 seconds. The value, currently adopted as Jupiter's official rotation period, representing the rotation of the planet's interior rather than its visible cloud tops. Saturn's rotation period remained uncertain for decades because, unlike other giant planets, Saturn's magnetic field aligns almost perfectly with the rotation axis, preventing the magnetic wobble that reveals rotation periods on other worlds. Cloud features rotate at different speeds at different latitudes due to differential rotation, so tracking atmospheric features yields different answers depending on which features are tracked. For years, The best estimate came from Voyager observations of periodic radio emissions, yielding a period of 10 hours, 39 minutes. But later observations showed variations in this period, suggesting it did not represent the true interior rotation. The Cassini spacecraft used multiple techniques to better determine Saturn's rotation period, including analyzing waves in Saturn's rings that respond to periodic gravitational perturbations from the planet's interior, and measuring oscillations in the magnetic field that revealed subtle asymmetries. The current best estimate suggests Saturn's interior rotates with a period of about 10 hours, 33 minutes, though some uncertainty remains. The difficulty in measuring Saturn's rotation illustrates how even basic properties of planets can remain uncertain when the most obvious measurement techniques fail, requiring creative approaches to extract information from subtle observations. Uranus rotates on its side with an axial tilt of about 98 degrees, meaning its north pole points roughly toward the Sun at one point in its 84-year orbit, while 42 years later, the south pole points toward the Sun. This extreme tilt creates the most unusual seasonal pattern in the solar system, with each pole experiencing about 42 years of continuous sunlight, followed by 42 years of continuous darkness. During the solstices, one pole basks in perpetual day, while the opposite pole sits in perpetual night, and the equatorial regions experience rapid day-night cycles as the planet rotates every 17 hours, 14 minutes. At the equinoxes, which occur twice per Uranian year, the Sun lies in Uranus's equatorial plane, and the day-night cycle becomes more familiar for all latitudes, with the terminator running from North Pole to South Pole, and all latitudes experiencing roughly equal amounts of day and night as the planet rotates. The equinoxes alternate with the extreme solstice conditions, creating a seasonal cycle that varies from familiar day-night rhythms to months or years of continuous day or night, depending on latitude and the current position in Uranus's orbit. The strange tilt possibly resulted from a giant impact early in Uranus's history that knocked it onto its side. Though proving this hypothesis requires better understanding of Uranus's interior structure and thermal properties. From Uranus's north pole during northern summer solstice, the Sun would circle around the sky parallel to the horizon, never rising or setting, slowly spiraling slightly higher and lower over the course of each 17-hour rotation, but never dropping below the horizon for 42 years. The Sun would appear much smaller than from Earth, only about 1/4 the angular size, since Uranus orbits 19 times farther from the Sun than Earth. The faint Sun would provide about 1/4% of the illumination Earth receives, roughly 400 times dimmer, comparable to the light level on Earth about 15 minutes after sunset on a clear day. After 42 years of this dim, continuous daylight, the Sun would finally set, initiating 42 years of continuous night at that pole, while the opposite pole entered its long summer day. Pluto and Charon are mutually tidally locked, meaning both bodies always show the same face to each other as they orbit their common center of mass, with a period of 6.4 days. From Pluto's Charon-facing hemisphere, Charon hangs motionless at a fixed location in the sky, slowly changing phase from full to new and back to full, as Pluto and Charon orbit the Sun and sunlight illuminates different portions of Charon's Earth-facing hemisphere. The phase cycle takes 6.4 days, synchronized with the orbital period, so full Charon always occurs when Charon lies opposite the Sun, as seen from Pluto. And new Charon occurs when Charon lies in the same direction as the Sun. From Charon's Pluto-facing hemisphere, Pluto similarly remains fixed in the sky. Much larger than the Moon appears from Earth due to Charon's proximity and Pluto's size relative to Charon. Pluto would appear about 7 times wider than the Moon, subtending an angle of about 3.5 degrees across, large enough to show visible surface details to the unaided eye. The phases would reverse compared to Charon's appearance from Pluto, with full Pluto occurring when Pluto lies opposite the Sun from Charon's viewpoint. The 6.4-day cycle would define time for any future inhabitants of these worlds, providing a natural calendar unit intermediate between day and month for Earth-based timekeeping. From the Pluto hemispheres that never see Charon, the companion world remains forever below the horizon, unknown except through travel or instruments. These far hemispheres experience a 6.4-day rotation period, defining day and night cycles. With the Sun rising and setting once per rotation, though appearing as merely a bright star rather than a disk, due to the vast distance from Pluto to the Sun. The stars would slowly rotate across the sky as Pluto rotates, and the distant Sun would move against this stellar background over the course of Pluto's 248-year orbital period, taking nearly 3 Earth centuries to complete one circuit of the sky through the constellations. Earth's rotation is gradually slowing due to tidal braking from the Moon, with the day lengthening by about 1.7 milliseconds per century. This imperceptibly slow change accumulates over thousands of years, requiring occasional adjustments to our timekeeping through the addition of leap seconds to keep atomic clock time synchronized with Earth's actual rotation. Atomic clocks, which measure time based on the vibration frequency of cesium atoms, keep nearly perfect time, independent of Earth's rotation, while solar time, based on Earth's rotation, gradually falls behind atomic time as Earth's rotation slows. When the discrepancy reaches about 1 second, a leap second is added to civil time to bring it back into alignment. The gradual slowing has been occurring throughout Earth's history, meaning days were shorter in the past. Geological evidence from growth patterns in ancient corals, which laid down daily and yearly growth rings similar to tree rings, preserves a record of how many days occurred in each year in the ancient past. Corals from 450 million years ago show about 410 days per year, indicating each day lasted only about 21.5 hours. The year duration has remained essentially constant over this time frame, so the change in number of days per year directly reveals how much the day has lengthened. Continuing backward in time, days were even shorter, with days possibly lasting only 5 to 6 hours during Earth's earliest history, when the Moon was much closer and tidal forces were correspondingly stronger. Neptune experiences seasons lasting about 40 years each due to its 165-year orbital period, with each season persisting longer than a typical human lifetime. The axial tilt of about 28 degrees, similar to Earth's 23.5-degree tilt, creates seasonal variations in sunlight reaching different latitudes, with each hemisphere experiencing long summer and winter periods, separated by equally long spring and autumn transitions. The seasonal changes drive atmospheric dynamics over multi-decade timescales, with cloud patterns and storm systems showing variations that correlate with Neptune's slow seasonal progression around the Sun. Observations of Neptune spanning several decades have revealed increasing brightness in the southern hemisphere as southern summer approaches, with more and brighter cloud features appearing. These clouds, composed of methane ice crystals, form at high altitudes where temperatures drop low enough for methane to condense. The increasing cloud activity suggests atmospheric circulation patterns responding to the gradually changing sunlight distribution as Neptune moves through its orbit. Understanding these long-period seasonal changes requires patience and long-term observation programs, with complete coverage of Neptune's seasonal cycle taking more than a human lifetime, making it a multi-generational project to fully characterize these diverse temporal patterns. From the rapid 9-hour day on Jupiter to the 42-year-long polar day on Uranus to the month-long day-night cycle on Venus, demonstrate how profoundly different the experience of time can be depending on a world's rotation rate, orbital period, and axial tilt. And understanding these patterns required centuries of observation and discovery that gradually revealed how our solar system actually works and what it contains. The knowledge we now possess about the solar system accumulated gradually through centuries of increasingly sophisticated observation, with each generation of astronomers discovering new details that challenged previous understanding and expanded the known boundaries of our cosmic neighborhood. Early observations relied on the unaided eye, limiting knowledge to the 5 visible planets and their motions against the background stars. The invention of the telescope in the early 1600s opened new possibilities, and each improvement in observational technique or spacecraft capability revealed unexpected findings that transformed simple points of light into worlds with unique characteristics. The pale blue dot photograph, taken by Voyager 1 on 14 February 1990 from a distance of about 6 billion kilometers, shows Earth as a tiny pale blue point of light, barely visible against the darkness of space and the scattered light in the camera optics. The image was requested by astronomer Carl Sagan, who recognized the philosophical value of seeing Earth from such distance, showing our world in cosmic context as a barely visible speck. Earth occupies less than 1 pixel in the image, appearing as a pale blue dot due to the scattering of sunlight by the atmosphere and reflection from the oceans, with no continents or other features visible at this scale. The photograph illustrates how small and isolated Earth appears from the outer reaches of the solar system, driving home the reality that all of human history, every person who has ever lived, every achievement and conflict occurred on this almost invisible point. The image became iconic for environmental and philosophical discussions about Earth's fragility and humanity's place in the cosmos. From Voyager's perspective, looking back across the solar system, Earth appeared unremarkable. Just another planet, slightly brighter than some and dimmer than others, notable only because we know it harbors life and civilization. Any alien astronomer observing our solar system from comparable distance would likely overlook Earth as an uninteresting terrestrial planet, unless they had instruments capable of detecting biosignature gases in the atmosphere. New Horizons provided humanity's first close-up views of Pluto in July 2015, revealing a world far more geologically active and visually complex than anyone expected. Pre-encounter expectations suggested Pluto would be a cold, dead ball of ice, heavily cratered like Callisto, showing little sign of geological activity. Instead, the first images revealed smooth plains completely free of craters, indicating very recent resurfacing. Mountain ranges reaching thousands of meters high, and a variety of terrain types, suggesting an active, complex world. The heart-shaped feature, named Tombaugh Regio, clearly visible even in low-resolution approach images, became the iconic symbol of the mission and transformed Pluto from an abstract point of light into a familiar world with recognizable geography. The smooth plains of Sputnik Planitia, the western lobe of the heart, show clear evidence of ongoing geological activity through a process called convection. The nitrogen ice that fills this basin behaves like a very slow fluid over geological timescales, with warmer ice rising from below and cooler ice sinking at the edges, creating a pattern of polygonal cells visible from orbit. Each cell measures about 20 to 30 kilometers across, with slightly raised edges marking the boundaries where cooler ice sinks. The absence of any impact craters on Sputnik Planitia indicates the surface renews itself completely within the last 10 million years, and possibly much more recently, perhaps within the last few 100,000 years, making it one of the youngest surfaces in the solar system. The mountains surrounding Sputnik Planitia rise several kilometers above the plains and consist of water ice rather than nitrogen. Water ice, at Pluto's extremely cold temperatures, behaves like solid rock, strong enough to support tall mountains without collapsing under their own weight. Nitrogen ice, being much softer even when frozen, cannot support significant topography and flows to fill low areas, which explains why it occupies the basin, while the highlands are water ice. The contrast between these two ice types creates the variety of terrain visible across Pluto's surface, with hard water ice forming mountains and ridges, while soft nitrogen ice fills plains and flows like glaciers in some regions. The first confirmed interstellar object passing through our solar system, named Oumuamua, was discovered on 19 October 2017 by the Pan-STARRS telescope in Hawaii. The name comes from Hawaiian and means roughly scout or messenger arriving from the distant past, chosen to reflect its origin from beyond our solar system. Oumuamua's trajectory showed it was moving too fast to be gravitationally bound to the Sun, approaching from the direction of the constellation Lyra, swinging around the Sun and heading back out toward the constellation Pegasus on a hyperbolic orbit that would carry it out of the solar system permanently. The object's appearance and behavior created scientific debate because it showed characteristics unlike typical comets or asteroids. Its shape appeared highly elongated, perhaps 10 times longer than it was wide, rotating end over end every 7 hours and showing periodic brightness changes as different surfaces faced the Sun. No coma or tail developed as it passed through the inner solar system, suggesting it lacked the volatile ices typical of comets. Yet it showed a slight non-gravitational acceleration away from the Sun, as if something was pushing it. The acceleration could be explained by outgassing of material heated by the Sun, similar to a comet, but no gas or dust was detected despite careful observation with multiple telescopes. The unusual characteristics led to various hypotheses about Oumuamua's composition and origin, ranging from a nitrogen iceberg broken off from an exoplanet similar to Pluto to a fragment of disintegrated comet. to more speculative ideas. By the time astronomers recognized it as interstellar and unusual, it had already passed close approach to the Sun and was receding, making detailed study difficult. It faded from view within weeks as it raced outward, becoming too faint for even the largest telescopes to observe. Future interstellar visitors will hopefully be detected earlier in their approach, allowing more thorough study before they fade back into the darkness beyond the solar system. The discovery of water geysers erupting from Enceladus came as a complete surprise when Cassini images revealed plumes emerging from the South Pole in 2005. Pre-encounter expectations suggested Enceladus would be a geologically dead ice ball, despite its bright surface, with any internal heat long since radiated away. The detection of plumes fundamentally changed the understanding of this small moon, revealing it as one of the most geologically active bodies in the solar system. Further observations showed the plumes varied in intensity with Enceladus's orbital position, being strongest at orbital positions where tidal stresses would be greatest, directly linking the eruptions to tidal heating. The decision to fly Cassini directly through the plumes to sample their composition represented a bold choice that paid off scientifically. The spacecraft's instruments detected water vapor, ice particles, salt, silica, and organic molecules, all erupting from an ocean in contact with a rocky core. Each plume passage added new details about the ocean's chemistry and the processes occurring at the seafloor. The detection of molecular hydrogen in particular suggested reactions between hot water and rock. Reactions that on Earth provide chemical energy that life can use, making Enceladus one of the most promising places to search for life beyond Earth. The James Webb Space Telescope, while designed primarily for observing distant galaxies and exoplanets, has also turned its powerful infrared instruments towards solar system targets, with remarkable results. Its ability to observe in infrared wavelengths allows it to see through dust and haze that blocks visible light, revealing details of atmospheric composition and surface features invisible to previous telescopes. Observations of Mars show seasonal changes in atmospheric chemistry, while observations of the giant planets reveal previously unseen storm systems and atmospheric circulation patterns. The detail available from JWST observations of relatively nearby solar system bodies far exceeds what earlier infrared telescopes could achieve. JWST observations of Europa detected carbon dioxide concentrated in specific regions of the surface, particularly in the geologically young terrain where the ice has been recently disrupted. The carbon dioxide likely originated in Europa's subsurface ocean and reached the surface through cracks and upwelling of ocean material, making it one of the strongest pieces of evidence for chemical exchange between the ocean and the surface. Understanding what materials reach the surface from the ocean helps scientists predict what they might find when future missions land on Europa and drill or sample the surface ice. Each JWST observation of a solar system body reveals details that help plan future missions and refine models of how these worlds work. The Beagle 2 lander, part of the European Space Agency's Mars Express mission, separated from its mothership on 19 December 2003 and entered Mars's atmosphere on 25 December 2003. But no signal was ever received after landing. The mission was declared lost, assumed to have crashed during descent or landing, with no way to determine what went wrong. More than a decade later, In January 2015, the Mars Reconnaissance Orbiter's high-resolution camera finally spotted Beagle 2 on the surface in the expected landing region, revealing that it had successfully landed intact but failed to fully deploy its solar panels. Images show the lander sitting on the surface, with only 3 of its 4 solar panels deployed, with the 4th panel remaining folded over the spacecraft. This incomplete deployment blocked the radio antenna, preventing Beagle 2 from communicating with Earth, even though it survived the landing. The discovery transformed Beagle 2 from a failure to a partial success, demonstrating that the entry and landing systems worked correctly and the spacecraft reached the surface safely. The lesson learned influenced future lander designs, emphasizing the importance of deployment systems with redundancy and clear failure modes that don't completely disable the spacecraft. NASA's Juno spacecraft, arriving at Jupiter in July 2016, carried instruments capable of imaging the poles for the first time with high resolution and invisible light. Previous spacecraft had viewed Jupiter's poles only at low resolution and oblique angles, never revealing the detailed structure. Juno's polar orbit allowed direct overhead views of both poles, and the first images revealed geometric arrangements of cyclones, completely unexpected by atmospheric scientists. At the North Pole, 8 cyclones arranged themselves in an octagonal pattern around a central cyclone, while at the South Pole, 5 cyclones surrounded the central cyclone in a pentagonal arrangement. These cyclone clusters persist stably despite the chaotic, turbulent atmosphere, with each cyclone maintaining its position relative to the others over years of observation. The geometric patterns emerge from a balance between the cyclone's tendency to merge when they get too close and the overall circulation patterns that keep them near the pole. Computer models of Jupiter's atmosphere failed to predict these structures before they were observed, and even after their discovery, modeling why they maintain these specific geometric arrangements rather than other configurations remains challenging. The discovery illustrates how much remains unknown about atmospheric dynamics, even on planets we've studied for decades. Neptune's atmosphere shows large, dark storm systems similar to Jupiter's Great Red Spot. But unlike Jupiter's long-lived storms, Neptune's dark spots appear and disappear over timescales of months to years. Voyager 2 observed a prominent Great Dark Spot in August 1989, a storm system roughly the size of Earth, rotating counterclockwise in Neptune's southern hemisphere. When Hubble Space Telescope observed Neptune 5 years later, in 1994, the Great Dark Spot had completely vanished, with no trace remaining at that latitude. In its place, a new dark spot had appeared in Neptune's northern hemisphere, showing that these storm systems are transient features rather than permanent structures. Subsequent Hubble observations revealed additional dark spots forming and dissipating over the years. Sometimes multiple spots visible simultaneously in different hemispheres or at different latitudes. The spots appear dark in visible light because they represent regions where the atmosphere is clearer than the surrounding areas, allowing us to see deeper into Neptune's atmosphere, where methane absorbs red light more efficiently. Bright companion clouds form near the dark spots, likely methane ice crystals condensing where air flows up and over the storm systems. The dynamic nature of Neptune's storms contrasts with the stability of Jupiter's and Saturn's largest storms, revealing differences in atmospheric dynamics between gas giants and ice giants. The bright spots visible on the dwarf planet Ceres puzzled scientists from the moment Dawn spacecraft's distant approach images revealed them in early 2015. As Dawn spiraled closer over the following months, the spots resolved into concentrated bright deposits within the crater Ocyta, contrasting sharply with the darker grey surface surrounding them. The mystery deepened when the high-resolution images showed the deposits had complex structures, with some areas appearing nearly pure white, while others showed streaky patterns suggesting material had flowed or been deposited in layers. Infrared spectroscopy revealed the bright material was primarily sodium carbonate, a type of salt mixed with other minerals. The salt deposits indicated that liquid brine had reached the surface relatively recently, carrying dissolved minerals from Ceres' interior. When the brine reached the surface, the water evaporated in the vacuum of space, or froze, leaving the dissolved salts behind as bright deposits. The concentration of the brightest deposits in the center of Ocyta crater suggests the impact that created the crater fractured the crust, creating pathways for brine from below to reach the surface. The presence of liquid brine implies Ceres' interior contains liquid water, or very salty solutions that remain liquid at temperatures below pure water's freezing point. Follow-up observations detected changes in the brightness of some deposits over the course of a Ceres day, suggesting some water ice remains mixed with the salt and sublimates when sunlight hits it, then refreezes when that area rotates into darkness. The discovery of recent and possibly ongoing brine activity on Ceres elevated it from an inert asteroid to an active world, with subsurface liquid and geological processes continuing today. Plans for future missions to Ceres include proposals to land near Ocyta crater and sample the bright deposits directly, potentially drilling into the surface to access fresher material, less altered by exposure to space radiation and vacuum. The discoveries continue with each mission and each improvement in observational technology, revealing that the solar system holds far more complexity and activity than anyone predicted when spacecraft first began exploring beyond Earth. What we know now differs dramatically from what was known 50 years ago, and what will be known 50 years from now will undoubtedly include surprises we cannot currently anticipate. Facts that will change understanding just as profoundly as these discoveries changed what came before. The Sun, the star at the center of everything we've explored, contains 99.86% of all the mass in the solar system, with all the planets, moons, asteroids, comets, and dust combined, making up less than 0.14%. This tremendous mass concentration creates the gravitational pull that holds everything in orbit. From Mercury racing around every 88 days, to distant Kuiper Belt objects taking centuries to complete a single circuit. The Sun's gravity extends far beyond the visible planets, reaching outward to the Oort cloud, where comets orbit at distances up to 1 or 2 light-years from the Sun, nearly halfway to the nearest star. The Sun releases energy through nuclear fusion in its core, where temperatures reach 15 million degrees Celsius, and pressure compresses hydrogen nuclei together until they fuse into helium, releasing energy in the process. This energy takes more than 100,000 years to work its way from the core to the surface, being absorbed and re-emitted countless times by the dense plasma between core and surface. Once energy reaches the surface, it radiates into space as light and heat, traveling 8 minutes to reach Earth, 43 minutes to reach Jupiter, and more than 4 hours to reach Neptune. Everything we see happening on the Sun's surface actually occurred 8 minutes ago, and if the Sun suddenly stopped shining, we would not know it for 8 minutes. The solar wind, a stream of charged particles flowing outward from the Sun's corona, creates a bubble called the heliosphere that extends far beyond the planets. This bubble represents the Sun's domain, the region where the solar wind moves faster than the surrounding interstellar medium and pushes outward against it. The boundary where the solar wind can no longer push back against the pressure of interstellar space is called the heliopause. And both Voyager 1 and Voyager 2 have crossed this boundary into interstellar space, reporting back measurements of conditions beyond the Sun's influence. Voyager 1 crossed in August 2012 at a distance of about 121 astronomical units, while Voyager 2 crossed in November 2018 at about 119 astronomical units. Beyond the heliopause, the spacecraft continue to move outward, still reporting data back to Earth, though the signals take more than 22 hours to make the one-way trip. The instruments measure cosmic rays, magnetic fields, and plasma properties in the interstellar medium. Data that cannot be obtained any other way, since this region is too distant for direct exploration by any other means currently available. Eventually, the spacecraft's power supplies will deplete as their plutonium fuel decays, and they will fall silent while continuing to coast through interstellar space. In about 40,000 years, Voyager 1 will pass within about 1.6 light-years of the star Gliese 445 in the constellation Camelopardalis, though by then it will be a silent artifact carrying a golden record with sounds and images from Earth. Earth occupies a position in the solar system that allows liquid water to exist on its surface, sitting in what astronomers call the habitable zone or the circumstellar habitable region. Move Earth about 1% closer to the Sun, and the increased heating would likely trigger a runaway greenhouse effect, similar to Venus, with oceans evaporating and water vapor trapping heat until surface temperatures climbed to inhospitable levels. Move Earth about 5% farther from the Sun, and temperatures would drop enough that oceans would freeze, potentially triggering a runaway ice age where the frozen surface reflects more sunlight, causing further cooling. The habitable zone represents a narrow range where conditions allow liquid water, though the exact boundaries depend on atmospheric composition and other factors. Earth's atmosphere extends much farther than most people realize, with the outermost layer called the geocorona reaching beyond the Moon's orbit during certain phases of the solar activity cycle. The geocorona consists of hydrogen atoms, so sparse they pose no resistance to satellites or spacecraft, but dense enough to be detectable with ultraviolet instruments. The Moon actually orbits within Earth's extended atmosphere by this definition, though the density is far too low to affect the Moon's orbit or to protect it from radiation the way the denser lower atmosphere protects Earth's surface. The geocorona represents the last trace of Earth's atmospheric influence, the final tenuous connection between our planet and the vacuum beyond. Oxygen in Earth's atmosphere creates a distinct spectral signature visible from space, a combination of absorption lines and emission features that indicates the presence of molecular oxygen at concentrations far higher than chemistry alone would produce. On a lifeless planet, oxygen would quickly combine with other elements and disappear from the atmosphere, requiring continuous replenishment to maintain high concentrations. On Earth, Photosynthetic life produces oxygen faster than chemical processes remove it, maintaining atmospheric oxygen at about 21%. This oxygen signature, combined with methane and other gases present in Earth's atmosphere, creates a pattern that astronomers search for around other stars, hoping to find worlds where similar processes might indicate life. The Sun does not rotate as a solid body, but instead shows differential rotation, with the equator completing one rotation in about 25 days, while the polar regions take about 35 days to rotate once. This differential rotation occurs because the Sun is made of plasma rather than solid material, allowing different latitudes to rotate at different speeds. The differential rotation winds up the Sun's magnetic field lines, like twisting a rubber band, creating regions of concentrated magnetic field that inhibit convection and appear darker than the surrounding surface, forming sunspots. The twisted magnetic field lines eventually become so stressed they break and reconnect, releasing energy as solar flares and coronal mass ejections. The Sun's activity follows an 11-year cycle from solar minimum, when few sunspots appear, to solar maximum, when sunspot numbers peak, and back to minimum again. The cycle results from the systematic buildup and release of magnetic stress, with the field completely reversing polarity each cycle, so that the full magnetic cycle actually takes about 22 years. During solar maximum, auroras on Earth become more frequent and intense as solar storms impact Earth's magnetosphere, while during solar minimum, auroras are less common and typically confined to higher latitudes. The cycle affects space weather throughout the solar system, though planets without magnetic fields experience the variations differently than Earth with its protective magnetic bubble. In about 5 billion years, the Sun will exhaust the hydrogen fuel in its core and begin fusing hydrogen in a shell surrounding the now helium core. This change will cause the outer layers to expand dramatically, transforming the Sun into a red giant star hundreds of times larger than its current size. The expanding outer layers will likely reach Mercury's current orbit and possibly Venus's orbit, engulfing and vaporizing these inner planets. Whether Earth survives depends on details of how the Sun loses mass during the expansion, since losing mass would allow planetary orbits to expand outward. But even if Earth's orbit expands enough to avoid engulfment, the intense heat would vaporize the oceans and strip away the atmosphere, leaving a scorched, lifeless rock. After the red giant phase, the Sun will shed its outer layers completely over about 100,000 years, creating a planetary nebula, a glowing shell of gas expanding into space, while the hot core remains behind. The core, no longer generating energy through fusion, will gradually cool over billions of years, becoming a white dwarf star about the size of Earth, but containing about half the Sun's current mass. White dwarfs shine only from residual heat, slowly fading over trillions of years until they become cold, dark remnants called black dwarfs. Though the universe is not yet old enough for any black dwarfs to exist, the solar system, or what remains of it, will orbit a slowly cooling stellar ember in the far future. The asteroid belt contains thousands of objects, but the total mass of all asteroids combined equals only about 4% of the Moon's mass, far too little material to form even a small planet. The belt occupies a vast region of space between Mars and Jupiter's orbits, But the individual asteroids are separated by such enormous distances that spacecraft can pass through the belt without seeing any asteroids close up, unless specifically targeted. The popular image of a dense field of tumbling rocks comes from science fiction rather than reality, as the true asteroid belt consists of scattered objects, mostly millions of kilometers apart. The reason the asteroid belt never formed a planet relates to Jupiter's massive gravitational influence during the solar system's formation. Jupiter's gravity stirred up the region, increasing collision velocities between planetesimals, until collisions destroyed objects rather than allowing them to accrete together. Jupiter's gravitational resonances also removed material from certain orbital distances, creating gaps in the belt called Kirkwood gaps, where almost no asteroids orbit. The material that remains represents leftovers from planetary formation, preserved examples of the building blocks that formed the terrestrial planets, making asteroids valuable for understanding the solar system's early history. New discoveries continue regularly, with new small moons being discovered around Jupiter and Saturn every few years as survey programs identify fainter and fainter objects. Many of these newly discovered moons are only a kilometer or two across, likely captured asteroids or fragments from larger moons, broken up by past collisions. The exact count of known moons changes frequently as new ones are found and confirmed, with Jupiter and Saturn currently competing for the title of planet with the most moons. Each discovery adds detail to our understanding of how moons form and how they interact with their parent planets and with each other. The Kuiper Belt continues to reveal new objects, with surveys finding dozens of new dwarf planet candidates in recent years, some on highly elliptical or highly inclined orbits that suggest gravitational perturbations from distant massive objects. The search for potential planets beyond Neptune continues based on statistical analysis of Kuiper Belt object orbits, though no ninth planet has been confirmed. Whether such a planet exists remains an open question, with some evidence suggesting gravitational influences from something massive in the outer solar system, while other analyses suggest the orbital clustering could result from observational biases or statistical fluctuations rather than an undiscovered planet. Each mission reveals unexpected details, even at worlds we thought we understood well. The InSight lander on Mars detected Marsquakes that revealed details of Mars's interior structure, showing the core is larger and less dense than models predicted, requiring rethinking of how Mars formed and evolved. The Parker Solar Probe's CLOSE passes through the Sun's corona measured conditions no spacecraft had ever experienced, revealing unexpected structures and behaviors in the Sun's outer atmosphere. The Juno mission continues to find new surprises at Jupiter with each orbit. From the depth of the Great Red Spot to the strange behavior of the magnetic field, to the discovery of shallow lightning in the atmosphere where it was not expected. What we think we know continues to evolve with each observation and each mission, with settled questions sometimes reopening when new data contradicts previous conclusions. The solar system we teach children about today differs substantially from the solar system taught a generation ago. And a generation from now, the picture will have changed again. Some changes come from new discoveries, like the geysers on Enceladus, or the active geology on Pluto, while others come from gradual accumulation of detailed measurements that refine understanding of processes and compositions. The journey of learning about our cosmic neighborhood continues actively, with missions currently in development or proposed for nearly every major body in the solar system. The facts we've followed tonight represent a sample of current understanding, a collection of remarkable details about worlds sharing the sun's light. Each fact connects to others we haven't explored, with each moon and planet and asteroid and comet holding more details than could fit into any single night's journey. The solar system continues to exist and evolve, whether we observe it or not, with volcanoes erupting on Io, geysers spraying from Enceladus, storms swirling on Neptune, ice flowing on Pluto. All these processes continuing in the darkness beyond Earth. The planets maintain their ancient orbits, the sun continues its fusion, the solar wind flows outward, and all of it persists as it has for billions of years. The exploration continues as well, with spacecraft traveling outward to new destinations, instruments observing from Earth and from orbit, missions being planned to return samples from Mars and to land on Europa and to visit asteroids and comets. Each observation adds to the accumulated knowledge, building a more complete picture, one detail at a time. What remains unknown exceeds what is known, with fundamental questions about origins and processes and compositions still awaiting answers. The solar system holds mysteries enough to occupy scientists for centuries to come, and each answer tends to raise new questions as understanding deepens. We live on one world among many, orbiting one star among hundreds of billions in our galaxy, in one galaxy among trillions in the observable universe. Yet the solar system represents our immediate neighborhood, the corner of space we can study in detail and visit with spacecraft. Understanding these nearby worlds helps us understand planets around other stars, revealing what's possible and what's common and what might be unique to our particular system. The knowledge accumulates slowly but steadily, with patience and careful observation. Year after year, mission after mission, discovery after discovery, building toward a complete understanding that remains always just beyond reach, but grows closer with each fact learned, each question answered, each world revealed in increasing detail. Beneath the same stars that have watched these worlds since they formed, and will continue watching through whatever future awaits them, through time that extends beyond human comprehension, in the silent darkness where the journey continues.